And you'll see people that put pictures on the internet like, what happened to my turbo? I didn't lose a valve. I didn't break a ring. I didn't lose a valve guide. I didn't do anything. But what the hell went through my turbo? Nothing, man. You ran it really hot and you spun it really hard, and your turbine wheel tips just spit off like a loogie. They just melted and just flew off.
Welcome to the HPA Tune-In podcast. I'm Andre, your host, and in this episode, we're joined by Robert Young from Force Performance and Xona Rotor. Force Performance in particular was one of the big names out there in the industry when I was getting involved in the car scene. They were particularly very well known in the Mitsubishi and DSM drag racing world. The initial turbos that Force Performance were producing were hybrid turbos using other factory turbocharger components, which at the time was really the norm. And this was born out of a requirement to try and find more flow than these factory turbochargers were capable of. Later on, Force Performance also became well known for taking what was at the time still a quality performance turbocharger from the likes of Garrett and replacing the factory compressor wheel with their own billet wheels, improving the performance well above what Garrett could ever produce themselves. More recently, Robert has joined forces with Greg Jones from Tial and they've formed Xona Rotor, now producing their own bespoke turbochargers, which are gaining a massive reputation for providing not only great response, but huge power potential. Before we jump into our chat, for those who are new to the Tune-In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build performance engines, how to tune EFI, how to construct wiring harnesses. We also cover topics on fabrication, 3D modeling and CAD, race driver education, and data logging, just to name a few. You can find all of our courses at hpacademy.com/courses. All of these courses are delivered in high-definition video modules that you can watch from anywhere in the world, provided you've got an internet connection. This means you can learn from the comfort of your own place and you can learn at your own pace. All of our courses also come with a 60-day, no questions asked, money-back guarantee. So if you purchase them for any reason at all, decide it wasn't quite what you expected, no problem, let us know. We'll give you a full refund. And for podcast listeners, you can also use the coupon code podcast75. That will get you $75 off the purchase of your very first HPA course. We'll put the coupon code in the show notes to make it nice and easy for you to find. Lastly, if you like free stuff, then I've got a great deal for you. We are constantly partnering with some of the biggest names in the aftermarket performance industry to give away some great prizes. You can always find our latest prize at hpacademy.com/giveaway. It might be an aftermarket ECU or dash. It could be some engine components or engine building tools, or just about anything in between. They are great prizes and we will ship them free of charge to your door if you're the winner. There's no tricks here, no purchase required to get your name into the draw. All right, enough with our introduction. Let's get into our interview now. All right, welcome to the podcast, Robert. Great to have you on board. I'm really looking forward to diving into the topics we've got in front of us today. You're a guest that I've definitely been looking forward to having a chat with. As we always do, let's start by finding out about your background, though, and specifically how you got involved in cars.
Well, thank you very much, Andre. Appreciate it. It's really nice to be here and finally get a chance to talk with you about turbochargers and the industry in general. I've never not been involved with cars. So just as a little boy, taking lawnmowers apart, and it just started there. Always just wanted to disassemble things. It's just how I got going. Always tearing it apart. The J.C. Whitney catalog, picking out a hot rod I wanted to buy in high school, not wanting to drive the car my dad gave me, having to buy a 66 Fairlane with a 390Y block in it. Just the only thing in my life I wanted was that Fairlane and that 390 V8. And it's just been downhill ever since then. I should have listened to everything he told me and done a completely different direction, but I didn't. And here we are. So, it worked out pretty good anyway. But basically just can't stand not having something to do with cars. Since I was a little kid watching the Dukes of Hazzard and Smokey and the Bandit, I just knew cars were going to be my bag. There was no way cars were not going to be my bag. I remember being a little kid saying, "Oh, wow, look, Mom, that's a 911S." And she'd say, "Oh, you don't know what that car is. Be quiet." And I totally did know what that car was. So.
I'm interested, the tearing things apart when you're young is a pretty common trait. I remember being involved in a bit of that myself. Out of interest, how many of those things went back together and worked ever again?
Yeah, very few initially. I had a neighbor that gave me a little pulse jet engine when I was probably in like the 6th grade. And I just remember staring at that thing going, I don't understand how it works. There's no moving parts to this. And I could see it had a little reed valve in it and, a little jet where the kerosene or the fuel would go in it and a little glow plug. And I just remember this is before the internet, of course. So like, I'm just staring at it, just going, I don't understand how it works. I don't understand how it works. And that mystery of not understanding how it works is really a huge motivator. Like for me, when I look at something and I can't understand where that glare is coming from on the wall over there. I have to look around for a shiny thing that made the glare on the wall until I can figure it out. So I just not understanding how something works always bugs me. You remember the little Cox RC engines, the tiny little ones, and they've got two exhaust ports on the side, right? Same thing. I'm staring at that as a kid, and I'm like, I don't understand how the air goes in and out of it. I don't understand how it makes horsepower. But I need to understand, and that need to understand and not understanding really drove me to go to the library as a little kid, check out a lot of books, and just read everything I could about cars. Today you would obviously be watching YouTube videos about it, and I don't know if that does the same thing to your mind as having to read it in a book and look at a illustration, a sectional drawing of something and try to imagine. I think it's different.
Yeah, it's definitely different. I mean, in a lot of ways, the current generation don't know how good they've got it. I mean, coming from my own background, again, same. Like when I was at school, the internet didn't exist initially, and it certainly, when it did start up, was nowhere near what it is today. And yeah, the library was the resource. I think one of the downsides with the internet today is, well, you've got all of the world's information for free at your fingertips. The challenge, of course, is understanding the difference between fact and fiction. Now, I'm not here to say that every book in a library is 100% factual. I'm sure that's not the case. But I would wager a bet that there's a higher percentage of accuracy held in a library than there is on an internet forum.
Yeah, it seems like it used to be hard to get a book made. The publisher had to believe in you, or somebody did, or you wouldn't have wrote the book. Humic and his turbochargers is there for a reason. Everybody looks at it because it's a great resource written by a guy that knew a lot about the subject. One of the pioneers in the industry for sure. And today there's just the signal to noise ratio with the internet is poor, very poor.
And I think signal to noise ratio is a really great way of expressing it because, as I say, there's definitely all of the information out there, but you have to dive in deep to find that.
And we've turned into a time period where, of course, everyone's opinion is very important. Okay. And
Yeah.
if I sound like I'm kind of making my head flop around when I say that, it's because I kind of am, because everybody's opinion might be important, but that doesn't mean what you think it means. The opinion of the guy that's got 60,000 hours of experience on the topic is different than the opinion of the person that's read an article about it. So,
yeah, I mean, it's been discussed multiple times on this podcast before, but I think the Dunning-Kruger effect comes into this as well, which, when you start into a new topic and start learning about it, your perceived level of knowledge and skill climbs very, very steeply, and the longer you're in it, the more you realize that you don't know what you don't know, and you start becoming a little bit more humble.
I don't know shit. That's what I know right
now. Well, I'm not entirely sure that I believe all of that, but we'll see. We'll see as we get further through this. That's probably a good point to segue into. Obviously, we've talked about you're sort of predestined to be involved in the automotive industry, but I mean, turbocharging is quite a unique aspect of that industry. So where did the passion and interest for turbocharging come from?
Air-cooled Volkswagen drag cars.
Okay, that's interesting introduction.
Watching air-cooled Volkswagen drag cars, reading Hot Volkswagen magazine in the 80s and realizing that the fastest ones were turbocharged. They were draw-through, carburetor, turbocharged, air-cooled Volkswagens. And that's where I really started to get the passion for it, for turbocharging specifically. And I started the magazines were a really big deal. So before there was D-Sport, there was Turbo and High Tech Performance magazine.
I remember that one. Yep.
Okay, so I read that all the time. I had every one of those, had every Hot Volkswagen magazine, and correlating the two things together. Like at the same time, Euro tuning magazines were starting to hit, And the idea of being like a P-car tuner and building custom Porsches, which is kind of like the Uber Volkswagen. If you're an air-cooled Volkswagen guy, you always have a lot of respect for the Porsche side of the family. You're just a college kid. You can't get there with your dollars. So, it doesn't keep you from lusting for it. So, all these magazines come together, and what they all showcasing is the incredible difference in performance that you can get when you turbocharge versus those small differences in horsepower you get when you spend a lot of effort making NA modifications to a motor. So you can spend a lot of money on cylinder heads. You can spend a lot of money on pistons. You can spend a lot of money on engine parts and make, oh, wow, look, we made 27 more horsepower. We changed the cylinder heads and we made 27 more horsepower. We changed the camshaft.
Kind of depressing, right?
Yeah, we made 41 more horsepower. And there was a time in the evolution of all this where when you change a camshaft and made 41 more horsepower, that was pretty cool. But if you turn the boost up 4 more pounds, you made 250 more horsepower. So
Yeah.
It's kind of really clear, like, did I want to get into the camshaft industry or the cylinder head industry or the turbocharger industry? And it was really clear that I wanted to get into the turbocharger industry.
I kind of see it as low-hanging fruit. I mean, obviously, if you're developing a turbocharged engine to the extreme, well, yes, you're also going to be doing heads and cams. But at the starting point, I mean, there's probably not a production turbocharged engine out there where you couldn't extract another 50 horsepower with nothing more than a little bit more boost. It's interesting, though, everything you've talked about so far is quite far removed from that Fairlane that you were lusting after. So where was the sort of U-turn in your direction for the cars that you were interested in?
Yeah, I sold a Fairlane. The Fairlane was impossible to work on. The 390 is so wide in the little Fairlane body, and I was a kid with a toolbox in the driveway, so it wasn't anything I could do with that. So that's kind of when I turned to the air-cooled Volkswagen stuff, and I realized that, wow, I could take the engine out of the air-cooled Volkswagen pretty easily. I can split this case and change this camshaft pretty easily. I can change these valves pretty easily. I can, change these carburetors pretty easily. And so that's really where I started to get a little bit more feedback from my effort. I started to get a little bit more, wow, look, I did it and it worked. Wow, I did it. I put it together and I drove it around. But that all ended when I went to college. So I went to school and went to start college in 1987, and I didn't know what to study at all. I didn't know that you could even have a career in anything cool like cars. It didn't dawn on me at all. I didn't know what to do. I was just totally lost. So I ended up studying film for a couple of years, cinematography and film editing. And then I saw my friends graduate from school and they were getting jobs as copier repairmen and bartenders and stuff like that. And I'm like, why do we go to school if we're going to be copier repairmen and bartenders? This is crazy. So I took a little while off school and started to think about things for a little while. And I realized I'm not a dummy. You're not a dummy. You can figure things out. You've always been able to figure things out. You've always said math isn't for you and science isn't for you, but I think you're wrong, Robert. So you should go back to school. So I did, and I studied physics for 4 years at Stephen F. Austin State University. And that's when I realized I could do complicated science if I applied myself. I wasn't the best at it. I was never an A student or anything like that. But the level of want to was great enough that I could do it and get through it. And I got towards the end of that physics program, and I started to realize, man, I'm about to be done, and I haven't studied any material science. I haven't studied any thermodynamics to speak of. I haven't studied any fluid flow. And so I left SFA and went to University of Houston to study mechanical engineering, and basically just had to start all over with the ME program there because none of the physics classes really meshed into the ME program. And I ended up spending another 3 years in the ME program, focusing on the things that I didn't get in the physics department. And it was during that period in Houston where I got a job in a machine shop, at a turbocharger machine shop. And so I started to realize that when I moved from one university to the other and I needed a new job, I thought, where am I going to get a job? I can pick where I want to work, right? Because I'm not an idiot. So I have some control over this. I don't have to cut meat or dig holes. I could do something cool. Look at the phone book out. Okay, which is crazy today. You didn't think you'd look for a job in the phone book. Get the phone book out, and I looked up turbocharger. There was like 4 companies there in the turbocharger section of the yellow pages. And I called them, and nobody was hiring. But I ended up getting one guy that, even though he wasn't hiring, he would talk to me. He was kind of a smaller business guy. And he had a little shop across the street from a Caterpillar dealership. So he'd get all the spin-off business for the people that didn't want to pay Caterpillar bills to fix their turbochargers. And I talked him into hiring me. And then I started to learn about turbochargers, how to build them, how to machine them, how to repair them, what the tolerances were. So I spent like 3 years there doing that while I was in the studying mechanical engineering. And so all these things kind of like really kind of like reach a critical mass kind of all at one time there. The last year I was in school and I was making so much money doing turbochargers that it was just clear that that was going to work really good.
Sure. So at this point, this company you're working for at the point here, this is rebuilding of stock turbochargers. We're not talking here about a performance application.
Yeah, they did in-frame overhauls of diesel trucks, and the turbos we did were like Navy turbo contracts for gensets and shrimp boat turbos and stuff like that.
Okay, but the technology, essentially the way the turbocharger works is the same, regardless if it's an OE
Totally.
non-performance item. Yeah.
Totally. The mechanics are the same. And while we were there, I realized that I could buy an Eclipse. So I bought a 91 Eclipse at the time. And so this was probably 96 or something. Wow, there's Mitsubishi turbos on these. And we didn't really work on many Mitsubishi turbochargers at the truck shop. But Fuso is a truck company that uses a lot of Mitsubishi turbochargers. So it was possible to get some larger TD06 Fuso truck compressor covers and some larger TD06 and 6H Fuso turbine wheels. And yeah, wow, the 20G compressor wheel is for Fuso. Wow. So I started to collect all these parts and realized, if these fit together. This TD06 and TD05 is not that much different from each other as far as the architecture of the turbo is concerned. And you could combine these parts in kind of hybridized fashion. And the guy that I worked with, Juan Garza, he started calling him, he's like, "You're like Frankenstein." I was like, "What are you talking about?" He's like, "No, you're like Dr. Frankenstein, man. You're mixing up all the stuff. You're not building the right part numbers." And it kind of stuck. We ended up calling the turbochargers Frankensteins. And when that company ran its course, I started Force Performance in October of '99 and basically just kind of took everything that I've been focusing on as far as specialized and customized Mitsubishi Fuso stuff and combined it with some Greddy offerings. And it was really hard to get parts at that point in time. You're talking about the late 90s, early 2000s. It wasn't like eBay was just full of copies of all the things I've built over the last 20 years like it is today. You can literally go build a kind of close replica of some of my turbochargers just by getting on eBay and ordering some parts right now. It's kind of crazy.
Yeah. Simpler times back then, perhaps. Just coming back to that, I cut my teeth on the Mitsubishi or DSM product range as well. And you're back in the days then, the range of offerings of aftermarket turbochargers that we take for granted today just wasn't there. And the TD06 hybrid on the factory TD05 was obviously a pretty popular option. And that 20G wheel obviously provides potential for more airflow. I remember one of the first hybrid turbos I got to deal with, though, instead of using a TD06 turbine wheel as well, which I guess in theory should be pretty well matched to a TD06 compressor wheel, the turbo specialist that we dealt with at the time would do what was called back cutting on the turbine wheel, which is sort of like machining the turbine wheels, the extruder on an angle to kind of open up the flow and kind of help match. How effective is that? I mean, obviously it's a pretty old school technique these days. You wouldn't probably do that.
It was done. We called it clipping here. When we used to do it, we called it clipping. And clipping has a history to it. It's not always done to increase flow. Sometimes it's done to just change the natural frequency of the blade so you can reduce long-term cyclic fatigue failures on the blades. It's typically how you'll see it implemented is when you have high cycle fatigue failures in turbine blades. The first thing they'll try is like, well, can we cut a little bit of the edge off of it and then change the tone that it wants to ring at? And then we don't have this high cycle fatigue failure problem. But at some point or another, people started to realize, wait a minute, if I get some of that turbine wheel out of the way, the flow rate goes up. And it does kind of help. It can help. And if you're limited and you're stuck with a certain turbine architecture, but you need to increase turbine flow, I mean, it's one of the only things that you can do as a rebuilder or in the aftermarket is to modify that turbine wheel by taking some of it off, clipping some of it out.
I do remember you sort of, when you're dealing with what is effectively a mismatch between OE components like that. The issue you do get into, we'll talk about this in a bit more detail as we go through, but you can run that turbocharger into surge because essentially you've got a smaller turbine wheel providing more turbo speed to a larger compressor. So depending on the engine, so I did strike that a couple of vehicles that I was involved with tuning, and I mean these days that really just, it's almost a thing of the past. Most people would probably never experience surge in their life with properly matched turbochargers.
Unless they're dealing with some sort of, aftermarket hybrid where you're stuck in a direct fit application and you're locked into turbine architecture, but you can change the compressor side. Sometimes you still encounter it there.
Sure. All right, so you just kind of decided one day that starting a performance turbocharger business was the next obvious move, which seems kind of brave. I mean, talk us through the sort of mindset you had then.
It was kind of brave, but at the time in the late '90s, I'd been building the Frankenstein turbochargers and what we used to call the list at dsm.org or MitsubishiTimes.org rather. The list. If you logged onto the list in 2000, or if you could go find a time machine freeze frame of that list from 2000, you'll see. And the top 20 cars, there's like 30% of them have my turbos on them.
So these things are selling themselves. If you want to be fast, that's what you need.
It was really kind of like, wow, when people talked to Robert and got one of his turbos, they ended up going a lot faster.
Just so we've got a reference, obviously as time goes on, cars get faster, but around that sort of late 90s, early 2000s, what sort of ETs are we talking with these DSMs?
Okay, if you could run mid 11s or low 11s, you had some respect, and if you could run mid 10s, you were a baller for sure.
Yep. Okay. So at this point, you're dealing primarily with that DSM platform and these Frankenstein OE-based turbochargers. Talk to us about how Force Performance sort of developed over time.
Well, you start to realize that you're trying to build all these turbochargers, and you're trying to buy Evo 3 turbochargers from Mitsubishi. You're trying to buy Fuso truck parts from Mitsubishi. I'm trying to buy all this stuff from Mitsubishi, and they didn't necessarily plan for there to be that many of those service products in the system, So what was for them a 49178 1470 Evo 3 turbocharger that they built for 1 year model car, what we build on, say you built 50,000 of those cars or whatever, so they built 70,000 turbochargers, 50 of them for the production and some for the support part system. Well, we used all the damn turbochargers up pretty quick. So they couldn't fill the orders for turbochargers. They couldn't sell us the Evo 316G turbos we needed. They couldn't sell us enough Fuso compressor covers. They couldn't sell us enough cartridges. They couldn't sell us enough of these parts. They just were not in the North American parts network.
You just cleaned them out.
Yeah, they just weren't there. So that's when we started realizing that we needed to start casting some of our own parts. And right about then, the Garrett Ballistic Concepts package had just came out. They just dropped the Garrett Ballistic Concepts. That was a guy, Todd Konecko, put that together in '99. Garrett released their ball bearing turbochargers in 1999. These were not billet wheeled compressor wheels. These were just normal cast wheels.
Is this the sort of first foray away from a journal bearing turbo towards ball bearing?
Yeah. So what we did was we realized that if we used those cartridges and compressor covers and we just made an exhaust housing that would fit the DSM manifold, then we would offer something that nobody had ever seen before. And I'd definitely never seen it. So we made a stainless steel exhaust housing. We call it the FP30 exhaust housing. I made it to fit the GT30 cartridge. And we ran 2 or 3 different part numbers of GT30 cartridge with like 52 pound a minute compressor, a 55 pound a minute compressor, and a 65 or 62 pound a minute compressor, the 3582 compressor that everybody used a lot of back in the day. And that was really popular. That let us attach a 500 horsepower ball bearing turbocharger directly to the DSM manifold. You have to realize at that point in time, using the DSM manifold was something that 95% of the people were doing. You couldn't just go buy a header. If you're going to get somebody to build you a nice stainless header, you're going to spend $3,000 on that and wait forever for it. Then you might say, today I'm still spending $3,000 on one and waiting forever for it. But you could also go to eBay and just buy, a mass-produced crappy tubular header and do anything you want today. It wasn't the option then. So having direct fit turbochargers at that point in time was really the only way forward.
So that direct fit option just opened up the aftermarket turbocharger option to a bunch of DSM owners that were just simply not in the market if you required a full, what we call today, a full turbo kit.
Yeah, because there was no manifolds.
Yeah.
Right, because there was no kits. There was no turbo kits. So you needed to be able to connect it to the manifolds you already had. You kind of needed your existing downpipe to work. So we made a little O2 housing that would fit with the normal downpipes that everybody already spent $600 on, and set a bunch more records. Man, everybody, and some of those. I think Kurt Brown set deep 9-second records on some of those models that happened later on. So that was definitely an exhaust housing that I made that had did a lot for the industry, did a lot for the niche.
How much of a challenge is involved in that process of designing and then casting a stainless steel exhaust housing? What was the learning curve like for you?
It was a lot steeper than I thought it was going to be. But this is also at the same time where I started my partnership with Greg Jones over at Tial Sport, because him being a manufacturer of wastegates and whatnot, he already had engineering software and design software that he was utilizing to design his wastegates already. So, and I just finished school, so I was kind of Mr. Software guy at the time, and SolidWorks was really popular, or becoming very popular at that point in time. So I kind of self-taught myself SolidWorks, and we started working on compressor wheels after we did exhaust housings. But Tial, the engineers over at Tial and Greg Jones basically helped me make my first exhaust housing. They made the tooling for it for me, and then we cast that housing at a foundry in Texas. As a matter of fact, this is way before anybody would just be thinking about talking to some communists about making parts for them. It was way before that sort of era. The world was a different place. The 9/11 hadn't even happened yet. So like the world was totally a different place, man. 1999, we were all worried that, that the electricity was going to go out because the Y2K problem.
Yeah.
I mean, it was a weird time.
It was a weird time. Look how that worked out. Absolutely fine.
Yeah.
I'm interested, sort of the direct fit turbocharger, obviously you're still stuck with this factory exhaust manifold. I mean, these days, of course, there's aftermarket direct fit exhaust manifolds that replicate the mounting location of the stock turbocharger anyway. But at that point with the turbochargers that you're offering, was the factory exhaust manifold anything of a restriction, or did it just not really factor in at that point?
That really wasn't a problem for 500 horsepower.
Yeah, okay. Yeah, makes sense.
Yeah, factory manifold didn't get in the way at 500 horsepower. Not in any considerable manner, no. We had even had some cases where we could operate, closer to 600 horsepower. Later on, we made the red model. We did operate at above 600 horsepower with factory manifold. But then I also made a manifold that emulated the factory form factor that had 15% larger cross-section area on the runners and a more well-crafted collector, and that helps make power too.
Sure. So at this point, you're talking about using a Garrett cartridge compressor wheel turbine in your own bespoke exhaust housing. At what point did you start actually producing your own FP turbos? FP green, FP red, FP black are the ones we sort of know and love. How did that come about? I guess, is this a case of there is a lacking or a problem or restriction in the offerings from Garrett, or is this sort of hedging your bets? Because I'm guessing that if you're still working with a factory Garrett off-the-shelf core, other people in the industry could look at that and go, I can see what Robert's doing here. Let's just make our own exhaust housings and we're off to the races.
Making your own exhaust housing was pretty hard at the time.
Quite a big barrier for entry.
It was, big barriers. Okay. It was no, I just got back from SEMA and I met 14 people that want to make exhaust housings for me. There was none of that. Okay. There was no way to do it. It was going to be a lot of engineering money up front, a lot of tooling money up front, and a lot of cost to make the exhaust housings. They were not inexpensive exhaust housings. They were not inexpensive turbochargers.
Okay, so it's not at this stage, it sounds like it's not a case of protecting your IP. So am I right in assuming then you saw a niche in the market that you could develop your own products around?
Well, we kind of had the green and the red model prior to, and then co-living with the FP30 models. They were kind of two price points.
Because those were a journal bearing turbo, weren't they?
Those were journal bearing turbochargers that were mainly out of Fuso truck parts. Yeah.
Okay. That's probably a good sort of segue into ball bearing versus journal bearing turbochargers. I kind of grew up with journal bearing turbochargers. They tended to wear, they tended to need rebuilds, reasonably frequent, sort of kilometre ranges, particularly when you're starting to run them down the drag strip really hard. One of the biggest issues I saw, though, with a lot of production turbochargers was the strength in thrust as opposed to the actual journal bearings themselves. They've got a sort of essentially a thrust washer. Some of them were only 180 degree thrust washers to make it nice and easy to assemble. Then there was other options to go to a 360 degree thrust washer, but they still weren't very strong when you started to up the boost levels and put more thrust loading into the turbocharger. So where are the sort of pros and cons with journal bearing and ball bearing turbochargers?
Well, you're exactly right about thrust limitations on the journal bearing turbochargers, and we recognized that before we ever got to the ball bearing stuff. Before we got to 2000 and used the Garrett ball bearing stuff, and that had led us to make custom thrust bearings for the Frankenstein and the green and red models from the very beginning. So a lot of times people look at rebuild kits on eBay and they'll go, "Oh yeah, look, that's what a thrust bearing looks like." That's not what a thrust bearing used to look like. That's what the thrust bearing looked like after I developed it for about 5 years. And then everybody in the world took them apart, looked at them and said, "Hey, that's how you make the good thrust bearing. Make it like that." So we did a lot to improve the thrust bearings, additional oil galleys, increases in the surface area, additional bias to flow to the thrust bearing, since that's so critical. These guys were running 35 pounds boost on these journal bearing Mitsubishi turbochargers and still having problems in some cases because the inherent limitation of the journal bearing turbocharger is its uninterrupted dependence. Its dependence on uninterrupted oil pressure. So if you've ever played that air hockey game where the puck, you turn the fan on and there's holes all in the deck and the puck floats up and you hit the puck back and forth, that game works really good because the fan is on and the puck is floating above the surface of the hockey table. So there's no friction there. But as soon as you turn the air off, the puck will not slide across the top of the hockey table anymore. Okay. Then you've got the same thing happening inside a journal bearing turbocharger. Optimally, none of those parts should touch each other.
I think it's kind of like it's no different to the bearings inside of your engine. I think there's a misconception here about how the bearings operate, but just like the thrust bearing, as you mentioned, there should be no metal-to-metal contact. You are actually have a layer of oil, and that's the protective layer. So that's critical.
And the operating condition of the turbocharger makes it even more perilous because the surface speed is way higher between the two parts that we're talking about in the turbo than it is on a rod bearing. Like order of magnitude, 10, 50 times faster surface speeds on the two parts as they go past each other inside the turbocharger than inside the motor. So if you have even 0.5 of a second where you didn't keep the two parts floated away from each other, they may have actually had 15 feet of contact with each other. Okay, be equivalent to like taking the little bearing and grinding it along the sidewalk for 15 feet with no lubricant between it. You might just do that in a half second. And so as soon as we started putting slicks on the cars and the suspension started getting dialed in and we started being able to run like 1.6, 1.5, 1.4, 1.3, 60-foot times, we started to lose journal bearing turbochargers just at the launch. Because if you sit there and stage the car, say you got 5 quarts of oil, you sit there and stage the car, you got to be ready to stage it for 7 seconds, right? So you sit there and stage the car for 7 seconds at 5,500 RPM two-step. Well, out of your 5 quarts of oil, there's 2.5 of them are in the valve cover right now. So now your oil level is about half what it should be in the pan because you've just been sitting at 5,500 RPM for 6 seconds, and that oil really hasn't drained back down yet. So then you drop the clutch and you move forward with a G of forward acceleration. You get a G of forward acceleration and a G of natural acceleration towards the earth. So the oil level's in a pan at a 45-degree angle in this analogy that I'm just describing. Well, did you or did you not uncover the pickup when you did that? Okay. And if you sample your oil pressure at a high enough sampling data rate, you'll see that you got bubbles going by there, during that 60-foot period. And you'll start scorching thrust bearings as a result of that. Now, in my mind, that singular aspect is the fundamental reason to use a ball bearing turbocharger, because the ball bearing turbocharger can tolerate intermittent oil supply. whereas the journal bearing turbocharger cannot tolerate intermittent oil supply.
And we sort of see that with the recommendations around oil restrictors to a ball bearing turbocharger. They really don't need very much oil to stay alive versus a journal bearing turbo. I mean, I'm interested, is there sort of a boost pressure, and inherently from the boost pressure, we're sort of talking about how that correlates to a thrust loading. Is there essentially a point which you're not going to get past with a journal bearing or a conventional thrust washer, and you have to go ball bearing, or can you engineer a thrust bearing to suit?
It's going to vary from frame to frame, and S400s you can get away with more than you can on TD04s or TD05s for sure. But as a general rule of thumb, if you're going to run more than, you need a really nice journal bearing thrust setup. If you're going to try to run more than 2 or 3 bar boost pressure, there's just no way around it. And if you ever run in 2 times the exhaust pressure that you are the boost pressure, then that's a big aggravator also, because you got to realize that that's also pressure on the thrust bearing. The back pressure is also pressure on the thrust bearing. So you're right in there where you got 2 to 1 back pressure to boost pressure. That's kind of a warning sign that you're going to have thrust bearing problems. If you're trying to run more than about 25 to 35 pounds of boost, that's probably an indicator that you could be susceptible to some thrust bearing problems with your journal bearing thrust bearing.
Now, I just thought while you're talking about that, for those who maybe are struggling to join the dots on what we've been talking about here, the thrust loading in a turbocharger, if you could sort of, obviously we're on a podcast, it's difficult to provide images here, but if we could imagine a cutaway of a turbocharger, when the turbocharger is spinning and producing airflow and boost pressure, essentially that compressor wheel is trying to drag its way out the front of the compressor housing. And likewise, as you mentioned, your exhaust flow is kind of doing exactly the same on the turbine, trying to drive the turbine wheel into the core or cartridge of the turbo.
You can get mixed forces on the turbine side, but I just wanted to point out that global issue. If the back pressure is just that much higher than the boost pressure, then yeah, you are going to get a resultant force all the way through.
So it's that thrust washer or thrust bearing that is there to stop that movement. Exactly the same as inside of an engine when we put our foot on the clutch, we need a thrust bearing inside of the engine to stop us trying to drive the crankshaft through the front of the engine.
Yes, and you'll see fellows with converter problems or really heavy manual clutches have problems with their thrust bearings sometimes also. Yeah.
All right. I think hopefully that's clarified it for people who weren't sort of aware of that. I think particularly when ball bearing turbochargers started to come online and become kind of the norm, there was a big sales pitch for the increased boost response that you'll get from a ball bearing turbocharger over journal. And my sort of take on it is probably more along the lines of the benefits being around that thrust bearing support being so much stronger. I'm interested in your take on that, particularly my guess is here in the smaller frame turbochargers where we've got less mass in the compressor and turbine wheels and less inertia. The benefits of faster spool on a ball bearing turbocharger might be realised. When we start to get to these big frame turbochargers with really big diameter compressor and turbine wheels and a lot of mass, I would have picked that that's maybe less of a consideration or benefit. Yeah, I'm interested in your take on that.
When you get really small, okay, you see that really small turbochargers, generally speaking, are not going to be ball bearing. Okay, you actually have some speed limitations on ball bearings as you get smaller. You really can't make precision bearings that small that'll do that type of speed. Okay, so when you see turbos like KO3s or KO4s or BO3s like you see on the 997s and the 991s and 992 whatnot turbochargers, those are all journal bearing because they have very small surface area bearings in them. They're really light rotors, and the loading is light. So the journal bearing can deal with it, and 3K does a great job on their thrust bearings and their little BV and BO series turbochargers. And so you don't see ball bearings when you go really small, but you also don't use really small, tiny turbochargers for 65 pounds of boost race car applications. So the two things fit. If you're trying to make 400 horsepower on a 3-liter sedan, then it works fine. Okay, but if you try to make 3,000 horsepower on a 4-liter sedan, then no, this is not going to be the approach you take at all.
Okay. Let's come back to Force Performance and just sort of fill out the scene here. So, I mean, if we kind of fast forward to today, can you give us the high-level overview of what Force Performance has become? So, for a start, size and location, whereabouts are you?
We're just north of Dallas, Texas, in a town called Van Alstyne. We're in a 2,100 square foot facility, 2 buildings here on about a 3-acre plot. We've grown to this slowly over time. When I first started, I was in a 1,200 square foot shed behind my house in 1999. It started very simply, grew very organically, and Bill really just kind of based my whole model on not being like some of the bad bosses I'd worked for and not making some of the mistakes that I saw other companies that I worked with do, and then just really try to focus on the product being the best quality product I could make. And then we had fortune too. Fortune was on our side. We had the birth of the internet, the birth of forums was happening right at the same time. Explosion in internet activity.
I'm guessing that your success on the drag strip with the Mitsubishi and DSM models probably didn't hurt either.
Bingo, man. Just having the results year after year, being on the fastest cars in that niche year after year. Now, focusing on that niche helped me, but it hurt me because, outside of 4G63, people didn't know who we were. So you get over in the Honda world and nobody's run a red model, and they don't need to, you know. So you get over to the Nissan world. The 300ZX, we did have offerings. We built T25 28s and T28s for the 300ZX. That was a popular model in the early years of it, but that didn't last very long.
Sure. I mean, these days, obviously, Mitsubishi have shut down production of the 4G63 years ago. There's a 4B11 that followed, but essentially they've moved away from that performance market as well. But before you sort of go further, though, just coming back to the business at the moment, so how many staff do you employ on site?
We run between 11 and 13 people usually.
And what level of the production is done on site versus relying on outsourcing, machining, etc.?
Well, a lot of the machining we do with our manufacturing partner, Tial. So a lot of the machining of the housings and stuff that we use is done in Michigan at the Tial facility, and that relationship, like I said, goes back to the beginning, the first exhaust housing we ever made. So our partnership on engineering and development goes back, to the 90s. So we don't really do finished machine work on a lot of parts in the building here. We basically have completely machined parts that I kind of make analogies. Sometimes we're kind of like a restaurant, right? We have ingredients to make everything on the menu, and somebody walks in and they say, I want the linguine. So you make it. That's kind of how we operate today. There's not a whole lot of, let's put 50 of this on the shelf and put 50 of this on the shelf and put 50 of this on the shelf. We like to talk to customers. We like to find out what needs are. We like to vary the product to fit the exact needs of the customer. And, a lot of times you just end up making a brand new part number because of what somebody needed.
Okay. All right. So how did you sort of spread essentially your product range outside of that Mitsubishi DSM platform? Where did you decide to go to next, and how's that worked out for you?
Yeah, in the early 2000s, you got to around 2003, 2004, 2005, you started to see that the STI was becoming a real player. Okay. It didn't look like it at first, but later on, the STI really, really blossomed into a great platform. So we started to build the same green and red models for the STI. The green model being your dual purpose street compatible, not going for 1 million horsepower, not also wanting to break the factory motor necessarily. So the green models, and then you had red models for, I need a higher output. I've changed the piston and connecting rods, and I have larger cams, and I want more power output. So we applied that same kind of stepped upgrade to the Subaru in the early 2000s and diversified into Subaru EJ 2.0 and 2.5 applications, and we still sell really deeply into the EJ and the FA20 market today.
I'm interested with that EJ market. Back when I was running my tuning shop, we kind of became known as Mitsubishi tuners because of my old drag car. So that was kind of our bread and butter. And we did a lot of 4G63 turbo upgrade packages. And at the time, obviously it was dependent on what the client wanted in terms of power range. But at the time, the Garrett GT3582 was one of our top picks. And on a stock engine, At the time, it was a good turbo. It maybe it hasn't aged that well. There's a lot of better options now, but we're talking at that.
Oh, for sure. But that was a 1999 release on the Ballistic Concept. So that was hot butter right then.
Yeah, 100%. I mean, at the time, with a set of 272 Calford cams, an ECU, an exhaust, an intercooled, that turbocharger, absolutely stock engine on pump fuel, would be sort of making 325 kilowatts, so what's that, about 440, 450 horse at the wheels on pump gas, 22 psi of boost, and that was our sort of go-to package. And I remember one of my first forays into the Subaru world. I had a customer with a GC8 EJ20 Japanese import, Japanese domestic market model, and he wanted similar power. I'm like, well, let's go. We know this turbocharger works on a 2-litre engine, and we kind of engineered that into the up pipe. And I mean, it's a bit difficult on a Subaru. There's a packaging constraints, but we got it in there, and I put it on the dyno, and man, was I disappointed. This thing made no boost essentially until about 5,500 RPM, and it was an absolute dog. So where I'm going with this long-winded story is, obviously you've got to size a turbocharger based on the application. There's a lot of constraints and considerations that go into this. For you, was it just literally a case of take that FP green, repackage it in a turbine housing that suits the Subaru and get the same results, or did my experience sort of mirror yours?
No, it was. You really couldn't look at the two engines equally. They're very different engines. The 2.5 displacement advantage, fewer people changing cams because there's 4 of them. There's a lot of differences between the EJ and the 4G63. And the green model and the red model for the Subaru do not have the same size compressor wheels as the green model and the red model for the DSM. We use the green, the blue, the green, and the red kind of as almost like lifestyle names for the turbocharger rather than a specific power level. It's just kind of small, medium, and large, really, is how that works. So medium on one application is not going to be medium on another application. And you need way more exhaust flow for the EJ25s than you do for the 4G63s. And a lot of times you do not want to run the EJs at the same boost pressure that you want to run the 4G63s at. So you got to get your rotor group set up to move more air at lower pressure ratios and take advantage of the V, the motor, and so on and so forth. So no, they're not the same, and you can't just transplant the build, the build of materials for the 4G over to the Subaru.
I'm glad that my experience wasn't in isolation there, and that you haven't just taken the same turbocharger, because I would have thought you'd have had pretty poor results. So it sounds like it's on the money.
Well, you start somewhere, right? And then you start to realize how wrong you're doing it, and then at some point or another, if you figure it out.
All right. Now, the other business that I want to talk about here, or turbocharging business, is Xona Rotor. Can you kind of give us a bit of a background on what Xona Rotor is and how that came to be?
Well, Xona Rotor didn't exist. And Greg Jones Tile Sport, and myself, we couldn't get all the parts we wanted from Garrett. I was buying a lot of Garrett turbos. Tial was buying a lot of Garrett turbos. We were modifying them. We had started to make billet compressor wheels at this point. And that's actually another sidebar story that's kind of interesting. Why did we start making billet compressor wheels? But we had been making billet compressor wheels at this point.
So these are still under the Force Performance banner, though?
This is still under Force Performance and Tial brands, at this time. But say you order 100 cartridges from Garrett, and you're supposed to get 25 of them a month for 4 months, and they just don't come, and you just can't get them, and they're just not sending them to you. So what you thought you were going to build 100 turbochargers, you get 4 months later, and Garrett hasn't shipped you anything.
It's hard to ship product when you can't get it in the door.
And it was a song that was not get off repeat and would not get out of our way. So ultimately, at some point, we decided that if we were going to not have turbos to ship, we should not have turbos to ship because it's our own damn fault, and not because we were dependent on somebody else. And so that just caused us to design the Xona Rotor X2B bearing system. And we first designed it for Mitsubishi application because that was a great application for it. We were trying to push the envelope to run higher and higher boost pressures. And we made prototypes of ball bearing Mitsubishi turbochargers. Mitsubishi took me and the turbochargers to Japan. They compressor mapped them for us. It was really cool. That was like 2011, 2012. But at that time, we were kind of transitioning away from using Garrett cartridges and realizing that we we were just really never going to get all the parts we wanted from Garrett, no matter how much we put on order. It didn't matter. And not that it was personal, it just was the way it was. And we couldn't get them. So we decided we would have to make stuff. And I was already making, at this point in time, this is, 2010, 2015 time period, I was already making a lot of my own turbine shafts and housings and stuff like that because I couldn't get them through the Mitsubishi parts distribution network anymore. So I'd already turned to making my own exhaust housings, first in Texas and then also overseas, because that's where Mitsubishi made them. Mitsubishi doesn't make any turbochargers in North America, and they don't cast any parts for turbochargers in Japan either. It's all done in Indonesia, Pakistan, India, Mexico. It's all done all over the place. Nobody ever has a foundry in their backyard. It's too stinky. Nobody wants it. So I've been making a lot of parts myself already, and we thought, we're making 80% of a turbo already. So why don't we make the other 20%, and then we don't need any cartridges or any housings or anything. Tial had been making V-band stainless steel nitronic housings for a decade at that point. We've been making billet compressor wheels for 6 years at that point. So really there was just a bearing system away from it. So we designed actually it's patented, variable preload angular contact bearing system for the X2B cartridge. And we went into production on that. And it's been very, very successful for us since we released it in, 15, I think.
Okay, a few follow-up questions on that. I think that makes perfect sense to sort of get, as you say, you've got 80% of a turbocharger that you're already producing, so why not vertically integrate and do the whole thing? I think with any business, the less you can rely on outside work or outside contractors or outside parts suppliers, the more control you have over the finished product. So yeah, that makes perfect sense to me. I would also say, though, just coming from a non-turbocharger specialist sort of perspective, that last 20%, the bearing cartridge, is probably the most critical and demanding part of the whole puzzle to put together. Am I kind of on the money there?
You're 100% right. And we came up with the most complicated, hard to make, high precision bearing systems that's ever been manufactured for a sports car turbocharger. The amount of pieces that are inside that bearing system and the way that they have hydraulic chambers to vary the preload of the races for low speed and high speed when you have low oil pressure and high oil pressure, that's just not present anywhere. And it is a very manufacturing intense process to build the pieces for the inside of this turbocharger.
Sure. It begs the question, I guess, where was the deficit in the existing Garrett ball bearing cartridges that you sort of saw a potential for an improvement there? Why not, I guess what I'm saying is, why not just blatantly copy the bearing technology that Garrett are using in their cartridges?
Well, we've always been less about copying and more about innovating. So, we saw the way that cartridge bearing is made, and the cartridge bearing at some temperature, it has the correct preload, right? Okay. At room temperature, it doesn't have enough preload. And at some high temperature, it has too much preload. Okay. But at some point in its operating range, it's got the correct preload. What temperature and when does that happen? And do you ever even operate it there? Okay. And then on top of that, the Garrett ball bearing turbochargers were made with a plastic style phenolic material ball spacer. So that was not very temperature resistant either.
Actually, I want to dig into this because this is something I could never get a solid answer to. So the Garrett ball bearing turbocharger range, they're a water-cooled cartridge, and there was a lot of debate, a lot of argument, a lot of misinformation around whether or not running water cooling was an essential for the Garrett ball bearing turbocharger. I always did it as a matter of course because it's there, why not? It's not that much of a ball ache to hook water up to it. But the rumour that I heard was that some of the Garrett ball bearing turbocharger cartridges use this sort of engineering plastic or phenolic cage for the ball bearing system, and others used metal. I never knew if that was true, but the sort of argument was if you didn't run water cooling with the plastic bearing cage, it would melt and the cartridge would fail. If it was a metal cage, no problem at all. Give me the actual story on that.
It's a true thing. Okay. The phenolic spacer has a weakness, and the failure mode is very specific. And it goes a lot like this. The phone's ringing, you pick up the phone, and the guy's like, man, you're not going to believe this. My car's been running so good, and I just go to back it out the driveway this morning, and the turbo's rattling around, and there's smoke and oil going everywhere. And I'm like, I do believe it. When did you drive it last? Well, I drove it last night, dude. I smoked 3 dudes on the interstate, man. And, constable was chasing me, and I shagged it into the garage and shut the garage real quick, turned it off, and I didn't fire it back up again until this morning. But man, I was hauling ass, man. And when I slammed that garage door shut, I couldn't believe how glowing my exhaust manifold and turbo was. But you got it off. It's sitting there glowing. Okay. So there's no water running through it at that point anymore. There's no oil running through it at that point anymore. And parts of the turbocharger were above 1400 degrees Fahrenheit. Maybe even the turbine blades were above 1400 degrees Fahrenheit. Well, the turbine blades are connected to the shaft, which is connected to the bearing, which is touching the phenolic spacer. So, you just can't take a piece of phenolic material. I don't care how awesome of a piece of plastic it is. It's just not going to do a great job when it's heat soaks to 1300 degree Fahrenheit. So what you see happen is, while the car cooled off after you turned it off, the spacer sagged and melted, and the balls kind of all rolled to one side of the cartridge assembly. And then tomorrow morning, you go and start the car, and now the cage that keeps the balls equally spaced all the way around is melted and all on one side, and all the balls are on one side. So the turbine wheel's on the other side. So as soon as you start it up, the blade starts rubbing and oil's going everywhere. And you're like, oh my God, I can't believe it. All I did was back out of the driveway, and actually all you did to find it was back out of the driveway. You did it yesterday. When it was glowing red. That's the failure mode for those things.
Yeah, mate, makes a lot of sense. And I guess the old story is that you never want to drive a turbocharged engine hard under high boost and then instantly shut it off, water cooled or not.
You never want to do that. Now some of us like jumped on the bandwagon, like my friend Lee Owen over at Owen Developments in the UK. He started making little bronze cages, so you could take the Garrett bearing apart and put in a bronze cage. We did that for a long time. And then ultimately Garrett released GTX. It's like, hey, we can make billet wheels too. We're a big company. We know how to do that. It's not just you cool aftermarket people. We can do that too. And so they did. And one of the things they implemented when they made GTX was they changed over to metallic ball cages. That solved that problem, really. Yeah.
Okay. Now let's come back to your variable preload. So, as you mentioned there with the Garrett turbochargers, your preload could be correct at some temperature. What are the implications of the preload being either not enough or too much?
Bearing wear. See, so when you need enough preload between the inner race, through the ball and through the outer race to keep the ball rolling. Okay, you don't ever want the ball to skid or slide in the race. So if there's not enough preload, then instead of the ball rolling, it just slides, and the race just slides on the ball, and the ball just slides in the race, and that makes heat, and that causes wear on the race surface itself. Now there's ceramic bearings, so the wear doesn't really happen on the balls. But in the beginning, the first Garrett ball bearing turbocharger was steel balls, steel races, and plastic cages. So that was really susceptible to having accumulated wear pretty quickly. Later on, metal cages helped with that, but still you got skidding going on. And then they never really changed their inner race material. They're using the same inner race material and outer race material. And turns out on a turbocharger, the inner race gets a lot hotter than the outer race because it's connected to the shaft. So what you want to do is you want to use a higher grade material on the inner race so that when the race is pressed onto a shaft that's at 800 degrees Fahrenheit, you're not going, oh, shucks, my material is not very strong at 800 degrees Fahrenheit. My material is very strong at 250 degrees Fahrenheit, but it's not that strong at 800 degrees Fahrenheit. So you have to select the right material for the temperature that you're going to operate at. And Xona Rotor does that. Xona Rotor has different material on the inner race, the outer race, ceramic balls, metal cages, and then variable preload. So when you're idling and you've got 30 pounds of oil pressure, you have 30 pounds of oil pressure in those little hydraulic chambers pushing on the bearing pistons. And then when you rev up and you've got 50 or 60 pounds of oil pressure or 80 pounds of oil pressure, now you've got 80 pounds of oil pressure in those chambers, and you have greater preload on the angular contact surface of the bearing. So you get greater control, more rigid control of the rotor group, and less bearing wear over time.
I'm interested in what the development process and validation of that cartridge, sort of how smoothly that went. Again, we're talking about a complex product with very fine tolerances.
It went through some stages, man, really. And like I said, before, we were the first prototypes of it were in iron Mitsubishi bearing housings. And so we really kind of cut our teeth during that phase of it, but we really hadn't released Xona Rotor yet either. So all those were just force performance turbochargers. So if they had problems with them or whatever, it wasn't our new brand. It was just, FP turbo braking, and it wasn't affecting what we were trying to do for our future flagship brand. So we cut our teeth on a lot of the problems during that first iron bearing housing phase from like 12 to 15. And by the time we released the Xona Rotors, more around 15, we had a lot of those issues sorted out by then. Kind of took about 3 or 4 years to really kind of understand what levels of precision and tolerance were going to work and were acceptable, what balancing procedures were going to achieve the results we wanted, and get it to where it's as reliable as it is now, and really a motorsports level turbocharger at this point.
All right, so I guess it does beg the question, why separate Xona Rotor out from Force Performance? Is this because of the closer relationship with this product with Greg at Tial Sport, or is it more a case of now you're talking a universal motorsport turbocharger as opposed to direct fit?
Well, Greg and I had a really similar dream, and it's neat. You're going to get to talk to him soon. If you're listening to me talk, you should listen to him talk too.
Yeah, on that point, we've got Greg on the podcast coming up very shortly, so that'll kind of, I guess, complete this conversation too.
I'm kind of curious to see how much his story is going to differ from mine, the way we remember it, because it's been a lot of time passed now at this point. But why is Xona Rotor its own company? We didn't necessarily want it to be complicated like that, okay? And, of course, I invited Greg to move down to Texas, and Greg invited me to move up to Michigan. But Greg's dad and his daddy are all from Michigan, and me and my dad and my daddy are all from Texas. I wasn't leaving, he wasn't leaving. So there really wasn't a way to combine forces. There wasn't a way to do it under one roof and us share the dream that we wanted, and both contribute our parts of the program towards the goal, other than to form a third company that we were just both owners of. And that's how it's done this way. And initially, Tial handled all of the manufacturing parts of it, the making of the intricate and high tolerance precision parts for the bearing cartridges, cutting the wheels, cutting the housings, et cetera, et cetera. And Force Performance handled the hot test stand evaluation, assembling the turbochargers, testing the prototypes, and collecting the data, and doing the after it's built part of it.
Okay. Yeah, well, that all makes sense.
Now it's all kind of balanced out. Now we build in both locations. So now there's just as many turbochargers are built in Xona Rotor, Michigan, as are in Xona Rotor, Texas now, if not more, a lot of occasions. Yeah.
Just sort of anecdotally looking at the results that people are achieving with popular, well-known engine platforms, swapping from other brands of turbocharger to Xona Rotor, I mean, it seems like you've got some kind of magic sauce going on here. You're getting more power for the same boost, along with better boost response or a lower boost threshold. I mean, those things, you've normally got that triangle and you can choose two. It seems like you've got a triangle and you've chosen all of them.
How do we have three? We spent a lot of money on development. Greg is really big on science, and we have spent a lot of money on software and product development, and we can thank the engineering department at Tial largely for getting this hard work done. It is very expensive to develop effective compressor arrows. It's very expensive to develop effective turbine arrows. It's a shame that things are as easy to copy as they are, because it really kind of makes you wonder why you're even trying so hard sometimes,
I guess these days, just to go on a tangent here, you're absolutely right. I'm assuming it's probably no more complicated than someone buying one of your turbochargers, pulling it apart, probably 3D scanning the compressor wheel, loading that into CAD, and straight away they've essentially got the ability to copy a billet wheel within 0.1% or less.
That you've hit one of the Achilles heels for everybody that invests money in manufacturing right now. Whether your Garrett in China copies your entire G line, of turbochargers, or whether you make drones and somebody leaves them in Afghanistan and now China's making the drones. Whatever industry you're in, if you're plowing the row, if you're the first guy down the line, you're gonna get copied, man. And if you spend even a minute trying to complain about it, people will mock you and tell you should have done it better. And if you didn't want people to copy you, then you should have done it for free. And you should be selling it cheaper. And if somebody else can make your part and sell it cheaper than you deserve to go out of business. And it's crazy the way that some people look at this stuff. It really is.
Look, I absolutely despise that sort of blatant copying of a product. I think there's a couple of things that we do need to kind of keep in mind with it, though. It's going to happen. You can't stop it.
I don't know what I can do about it. It's not the Wild West. It's not like you can form a posse and ride over there and string them up or anything.
I mean, I don't think it's something that you put your head in the sand and ignore. I mean, absolutely, it's worth fighting, but you're probably going to be a losing battle with nameless companies and entities in China, Taiwan, or wherever the hell they may be. I mean, these are going to be very difficult to legally prosecute. So it's kind of a given in the industry. What I would say, though, is that you're almost certainly continuing to innovate.
We're not going to stop doing it. And like I said, we spend a lot of time, we spend a lot of energy, we spend a lot of money, blood, sweat, and tears on making new, higher performing compressors.
So these imitators are always going to be one step behind, essentially.
You're always going to have to chase us, and then you're always going to be wondering what's special about this part that makes it work. And you're not going to pick up on all of it quick enough to really make it work. So we just stay ahead of everybody by staying ahead of everybody. You win by winning at the end of the day. So why do we seem like we always have to have the cake and eat it too? We have multiple wheel arrows. Okay, like if you were to look at another turbocharger company and they have a whole line of turbochargers, do they have 3 different 80 millimeter arrows? One for super high pressure ratio, one for middle, and one for 20 psi Vipers. We have multiple arrows for multiple aerodynamic applications. We spend a lot of time worrying about drive speed matching, turbine speed matching compressors, and making sure that you got the effective range of the compressor matched up with the effective range of the turbine wheel. We find that the speed match is really critical in getting all 3 of the things, as you put it. Not leaving something out, not having to do without something. If you've got a proper speed match between when the compressor has its sweet spot and when the turbine wheel has its sweet spot and when the motor and camshaft and VE has its sweet spot, if you get all those things sweet spotted right on top of each other, you do get the faster spool, you do get the greater peak horsepower, and you do get the improvement in overall system efficiency.
I just wanted to take a moment out of our chat with Robert and talk about a course that's really relevant to just about anyone involved in turbocharging, and that is our boost control tuning course. Normally valued at $79, you can use the coupon code FORCED25. That'll get you $25 off the purchase, bringing it down to just $54 US. Now, boost control is probably one of the things I see most people struggle with when it comes to setting up turbocharged engines, and of course, if you get it wrong, you could end up doing some very expensive damage to your engine. It's not that difficult to get it right, but we do need to understand the principles, the fundamentals behind boost control. And this comes down to not only the mechanical setup of the wastegate and turbocharger, but also the electronic system that's controlling it. We start by discussing one of the topics that I know a lot of novice and experienced tuners alike struggle with, and that is PID control. This is the backbone of electronic boost control. And if we don't understand how the proportional, integral, and derivative gains work and how they interact, then we have absolutely no chance of getting stable, accurate boost control. We then move on to the fundamentals of boost control. We cover boost control itself, wastegate operation, and wastegate spring selection. We talk about internal versus external wastegates, boost control solenoids and how these work, as well as our boost control plumbing. And we cover open loop versus closed loop boost control and the common control problems we see. We then move into the boost control tuning process and how we should approach this. And then we've got some worked examples where you can actually watch this being applied in real time on a real boost control tuning job. As mentioned, you can use that coupon code FORCED25, get $25 off the purchase. You are still protected by our 60-day, no questions asked money-back guarantee. And you can also break that purchase down at the checkout into as many as 8 individual weekly payments. You'll find a link to this course as well as the coupon code in the show notes. For now, let's get back to our chat with Robert. All right, just coming back to one of the points you've made, and I'm going to play devil's advocate here. You mentioned that you're putting a huge amount of time and money and resources into developing the aero of the compressor and turbine wheels, and I don't doubt that for a second. The results speak for themselves. However, I'd argue that without knowing too much about you and Xona Rotor, I'm going to guess that probably Garrett are a little bit more financially resourced than you guys are. So why is it that you are able to essentially beat them at their own game? Or is this a case of Garrett's focus is so primarily around producing turbos for the OE market and their performance or motorsport range is kind of a drop in the proverbial ocean?
Well, first of all, I love to see other people do it wrong, and I'm not ever going to rush out and tell them how to do it right. Okay, so when I see my competition fighting with my other competition, I stay out of it. Okay, so when I see Garrett try to do something better than PTE and PTE trying to do something better than Borg Warner or however it goes, I leave that alone. I don't worry about it at all. Why would Garrett, that has, comparatively a limitless budget for developing things, why would we be able to have better models than them? I think it's because Greg and I are living our dream with this company by making the best turbochargers that we can. And I'm in my mid 50s. Greg's a few years older than me. We're not spring chickens when it comes to making cars go fast with turbochargers. And whether that's a land speed, missile rocket car, or whether that's a Pikes Peak car, or whether that's a quarter-mile motorcycle, whatever the case, snowmobile, whatever the case is, we have a great perspective on how to get what that motor needs to that motor as far as turbine and compressor sizing goes. So, when you see Garrett just go, hey, we've got a whole new array of turbochargers all the way from 55 millimeter to 98 millimeter. Well, what did those get designed for? What is the target application for those? So a lot of times people just, you just wish that, I don't know. I don't want to just sit here and talk about how Garrett can improve their product line, but there's ways they can improve their product line for sure.
Yeah.
The things are just not sized right. They get locked into corners where they go, we want to make this a bigger turbocharger. So they make a bigger compressor, but they don't make a bigger turbine, and it doesn't speed match well, and it doesn't work well. And it's got a great compressor map, but you can't use but 3/4 of the compressor map, because that other quarter of the compressor map you can't get there with that turbine wheel. So they're rated 1,600 horsepower, but like nobody ever makes more than 1,350.
You'll never get there.
You'll never get there. So it's just because we try harder and we're better at it. That's the answer. You get into corporate America and, there's somebody named Susie that runs this department, and, it just is what it is. At the end of the day, we all punched in, punched out, and went home. Greg and I just never go home.
There's a lot to be said for just working harder than the next guy or girl, I think.
Yeah.
All right, I just want to talk about kind of the development process for your compressor wheels, and I suppose this really flows into the turbine wheels. We've sort of already talked a little bit about the technology. I mean, the aerodynamics of these wheels, obviously so critical to their performance. So how are you developing the shape of these blades, the number of blades, etc.? What software are you using? I'm assuming there's a lot of CFD going on here.
There is a lot of CFD. There's a lot of flow analysis. There's a lot of stress analysis. There's a lot of let's calculate this and we'll see what the answer is day after tomorrow. That happens. And it's a lot of iteration. There's a lot of iteration, and then there's a lot of testing. So you design something, you revise something based on what you've already had and how you want it to change better. You make revisions, you run the analysis on it. If it looks promising, then you refine it a little bit more, and until the engineering data shows that it should yield these sort of results. Then you make some and you test them. You hot gas test them. You have some engines, you might engine dyno or even track dyno or chassis dyno just to a final evaluation of them. But essentially, it's a lot of software analysis, then it's a lot of hot gas test stand analysis, and then it's a lot of on-car analysis.
Okay, I'm going to dive into a couple of those points in a second, but in terms of that process, I'm far from an aerodynamicist, so I'm kind of out on a limb here. Is that iteration process that you talked about of design, CFD, validation in the virtual world, is that all manual, or do we have the options now? I'm going to kind of compare this to generative design in CAD, where you can basically feed your CAD system a set of metrics that you're trying to target and then let it go for gold, and it's going to come up with a generative design for your part that kind of meets your design criteria. Is there anything that exists around development of aerodynamics for a compressor wheel like that, or is it literally just tweak it and see manually?
There's not an AI aspect to compressor wheel designing where you can say, hey, I want to improve this about this, Mr. Software, please make this part of this better. You have got to lead your program with your own insight, and you have got to find the things that you want, the geometry you want in the wheel, and then you've got to see what the result is. So there's not I don't want to keep saying AI over again, but there's not an automatic way that it can really happen.
I'd argue that's probably a great thing for you, though, because the fewer barriers there are in the way, the more people are going to be able to do this. I mean, I guess it begs the question while you were talking, though, is this coming with, obviously, 2024, all we're hearing about every week is AI this, AI that. It would seem like potentially at some point, maybe down the line, there is the potential to incorporate AI to do exactly what I was talking about, basically automatic iterations.
It seems like that's what they're selling AI as a solution to. Large, difficult to nail down problems like that. But I think at this point, AI still fails to do a good job of that. If you want to fly a flock of drones up to somebody with particular facial recognition pattern and then blow that person up, I think AI will do a good job of that. But I don't think AI can do a good job of designing a better compressor wheel. Not today, anyway.
Okay. You've talked a couple of times now about a hot gas stand. I think there's a term you mentioned. So
yeah, hot gas test stand.
Mm-hmm. Okay. Explain this hot gas test stand and how it's used and what it tells you.
Well, it basically takes the place of the engine. So you don't need an engine to operate the turbocharger. And you are able to, when you test stand a turbocharger, you'll get the turbocharger to a specific RPM, okay? And you will move through the different possible pressure ratios and mass flow rates that RPM can deliver. So you'll move from one end of the line to the other end of the line. So you might move from the choke flow line over to the surge line, or you might move from the surge line over to the choke flow line, depending on what you're trying to achieve or what data you're trying to collect or validate. So like say you have a turbocharger and it's supposed to have improvements in mass flow rate above 60 pounds a minute and above 4.5 to 1 pressure ratio above the other design. So what are you going to do? You're going to put it on the stand, and you have a huge air factory. So you have like a very large diesel engine powering a very large air compressor, and that provides air to a burner, like a jet engine burner, okay? And then you control the output of that burner by throttling it and by delivering propane to it. In our case, we use propane. And that's burned in a combustor that is basically a jet engine combustor, part of a jet engine for an aircraft. And then that output goes into the turbine inlet of a turbocharger exhaust housing. And then with gates and valves, you will get that turbocharger operating at the flow rate and pressure ratio that you want by adjusting the fuel delivery from the combustor and then the compressor inlet and outlet valves to achieve the pressure ratio and mass flow rate that you're looking for. And you got like a 10-foot long tube off the front of the turbocharger with a bunch of little pipes sticking on it and hoses connecting all around. And you have to really go out of your way to collect data in the most accurate way possible. Okay, so you don't just drill a hole in the side of the tube and connect a vacuum nipple to that and go, that was the pressure inside the tube. You drill 6 tubes, you drill 6 holes on the tube, and you gang all 6 of those holes together. And then you send that balanced 6 port into one signal line to a sensor that's more accurate than an average sensor you'd use in a car. And that's how you get your level of precision that you're at. You need a lot of significant digits when you're doing this sort of analysis, using a $40 sensor that you would put on your car. Mass flow sensor is also very expensive at this level because you're very precisely measuring the airflow to the turbocharger.
So essentially, this test stand allows you to produce your compressor map, essentially.
Correct. And you basically use the software and the stand back and forth with each other to develop a new compressor.
So this test stand, are you doing this in-house? So it sounds like a pretty expensive piece of equipment.
Yeah. I built it. I just built it myself. I didn't want to. There's not really. You can go to Walmart and buy one.
No,
they don't have that at Target or the grocery store. So mine's built. My test stand runs on an M800 with an expander box. I've got the only 12-volt test stand in the world. I promise you.
Wow.
Because I started trying to do this project on my car. Okay, and then I realized I was like, I'm going to die. I'm just going to die. Okay, trying to get this speed line on this deserted airport runway. I'm going to die. Trying to get this 125,000 RPM speed line. So we were like, we need to do this, but not have it in a car. So.
Well, I think it takes away just the variations that come with an engine. And the other thing is, I've talked about this before on the podcast, but we had a Toyota 86 FA20 engine, stock engine with a little Borg Warner EFR 6758 turbocharger on it. And just because I'm a bit of a tech nerd, we kind of set up all of the sensors with compressor inlet and outlet temperature, compressor inlet and outlet pressure. I wrote some code in Motec M1, and lo and behold, it pumps out adiabatic efficiency. And it was more for my personal interest, like, can I do this? And yeah, I could. But what I quickly found as well, when you did that test, 3,000 RPM steady state, it takes quite a long time for everything to sort of reach equilibrium and you're actually getting results. So, I mean, I'm sort of thinking, I did this at 3,000 RPM, maybe 0.7 bar of boost. If you wanted to test that thing at 8,000 RPM and 3 bar of boost, the poor engine.
Yes, you're gonna destroy things.
Yeah.
Yes.
Yeah.
And you destroy turbochargers doing the mapping too.
Yeah, no doubt.
Okay, because like if you want to make a speed line and you want to check, say you want to check 24 points on the speed line because you want to define compressor efficiency, that's 20 something odd points where you're going to operate for about 5 to 10 minutes until the data totally gets to equilibrium and stops changing, like to within less than 1%. So you're going to watch that compressor outlet temperature change from the previous operating point to the new operating point. But as it gets closer and closer to being a stable temperature, it takes longer and longer for it to make that last little bit of change. So it's particularly sketchy when you're doing the high RPM close to the surge line stuff. That's when you'll end up breaking turbochargers, because if you're trying to go from choke flow over to the surge line while you're doing the high speed line, how do you find the surge, right? You almost find it when you break the turbo.
It's one way to find it.
So compressor maps end up being really expensive things to make. They eat turbos up. You have to build a stand. You need lots of super expensive software, and then you need a PhD guy to run the software for you. So.
How well do things stack up on that test stand based on the sort of the CFD? Are we talking that everything just correlates perfectly, or do you kind of get some surprises?
It didn't always. It doesn't always. And so what you end up doing is you have to use what the math says is going to happen and compare that to what actually happened in the real world. Usually they're not very far off. And when you're doing the math, alpha, beta, gamma sort of factors involved in doing the math anyway. So instead of using a correction factor of 0.7126, you end up using a correction factor of 0.7124. That actually made the simulation match the real world better. So you can't just do it all in software because you're not going to actually have the answer. You're just going to have what the computer thought. You're not going to actually have what really happened. So you can't just get all tied down into, wow, we spent $750,000 on some software. We don't have to do anything else anymore. No,
not that easy.
Not that easy.
In terms of the construction of the compressor wheels, particularly, billet compressor wheels have kind of been a must-have of the aftermarket performance turbocharger industry for, I don't know, probably at least a decade or more now. What's the reality of that? I've sort of seen it as more a case of you could build any turbocharger compressor wheel as a cast item, but billet lends itself to small run sort of production better than casting. Is there a case of these wheels could not be built any other way than billet, or what's the situation?
Okay, there's two totally unrelated things there that you hit on that are both right, but they don't exclude each other. Okay, and that's can you machine surfaces that you can't cast, and can that get you an improvement in performance? That is possible. Yes. Okay. And then the other side of that was like, do you just avoid casting sometimes, even to make a mediocre wheel, just because of production limitations like tooling costs? And wow, we really only need 150 of these. We've got a customer named Koenigsegg, and they're not making a bunch of this, so we'll just cut them all instead of casting it. So there's definitely both of those things are true. How did we come to start making billet compressor wheels in the first place? It was the damn Evo 8 is what made us do it. My standard process of taking Frankensteining other heads onto the bodies of the existing turbocharger wouldn't work in the case of the Evo because it turned backwards.
Ah, yeah, of course, reverse rotation. Yeah.
So where am I going to get a donor compressor wheel from? Fuso doesn't give a crap about having a reverse rotation, which way the turbo turns. They've got a diesel engine compartment with a flip up cab. They got plenty of room. There's no packaging concerns going on. There's no motivation for one that turns the other direction. There's no parts made. So there was no other parts to adapt when it came time to make upgraded Evo 8 turbochargers. So that led to us having to cut compressor wheels. And this was 2005 when we started cutting compressor wheels. Okay. Which is a long time ago. If you think about it, that's like 19 years ago now. But that's when Greg first started cutting compressor wheels for turbochargers. Was that long ago. And it was out of the first thing you talked about. Wow, low volume manufacturing. How do we ease the entry expense of low volume manufacturing? And if you already have machines that are capable of doing it, well, then your entry fee is really low. You just have the design and the engineering time. So that's how we started making billet wheels. And then after that was successful, we were like, wow, we made something that works good. What if we actually spent a lot of money on engineering? Let's do that now.
Let's see where this can go to.
Yeah. So now we've got something cool. Wow, look what this thing does. Let me see what everything it can do. And so we started spending money on aerodynamic engineering for the wheels, and we made the first HTA wheels, and we started putting those into GT30 and GT35 cartridges, making things that we called 3582 HTAs and 3586 HTAs and 3794 HTAs. And those ruled the land, man. Those ruled the land. That before we did that, PTE did not have billet compressor wheels. Before we did that, Garrett did not offer billet compressor wheels. Before we did that, nobody offered billet compressor wheels. We, Greg and I, were the first people to put billet compressor wheels into aftermarket performance turbochargers. That didn't exist before this.
And all led by that necessity of the Evo 8.
That was the catalyst for it.
It must have been quite satisfying with those HTA wheels, though, to take a product that Garrett made and then actually be able to get a significant improvement.
Oh, it was nice, especially, they take you to dinner at SEMA and stuff like that and buy you steak, and, you're the hero because you're stealing all the sales from PTE and stuff like that. But then 2 years later, they released their own billet wheel turbos, and they go, oh, hey, we have billet wheel turbos now. You don't have to make yours anymore. They're like, yeah, we're still going to make ours. But then they made sure we couldn't make ours because we never got any cartridges anymore. So.
Yeah, that makes it pretty tough. One way or another, you're not making them for their turbos.
Yeah, so when they told us you don't have to build yours anymore, they kind of made sure we didn't get to build ours anymore. Then we just started, like I said, we made the whole damn thing at that point.
Other advantages, as I see it, with billet would be the consistency and strength of the material. I'm just wondering, at extremely high pressure ratios, do you get to a situation where a cast compressor wheel is marginal in strength and billet really is the only option?
There are very high strength cast wheels out there, and there's procedures you can do with castings to even make them denser grain structure and even stronger than you would think they should be. And the diesel industry is full of it. There's a heat inducted pressure process, a hipping process that you use for aluminum compressor wheels that really does increase the strength of them. And that's very common in high pressure diesel applications. You do see billet being used in high pressure diesel applications now, as well as titanium. Okay. In some applications, titanium has its own problems, though, because if you were to burst it, it's a much more dangerous burst than an aluminum compressor wheel burst. I mean, it's bursting inside an aluminum housing instead of bursting inside of a big iron housing. So your containment issues for OEMs become worrisome. And containment as a whole, you could spend 2 hours talking about containment problems. But mainly in our experience, one of the things that we like most about billet wheels is the flexibility of manufacturing, the way that we can achieve the specific low volume runs of stuff that we want to do for different applications. And when we talk about the limitations of normal wheels, usually they're not pressure ratio based as much as they're RPM based. Okay, so it turns out blade loading due to pressure ratio is there and it's significant, but hub loading due to centrifugal force of the thing spinning is just dunks that other concern out of the way completely. The biggest problem you have with compressors is not that the blades bend. The biggest problem you have with compressors is that you spin them to the point where they shatter into three pieces. You have a tri-lobe failure of a compressor due to spinning it too fast. The same reason they don't let you use cast iron flywheels at the drag strip. The same reason you have to have a burst containment over your automatic transmission or over your clutch in racing applications is because if you spin anything fast enough, it will explode. Have you ever seen the videos where they take a CD-ROM and then they, instead of putting 5 volts to it, they put 48 volts to it and they spin it until the CD explodes?
I have not. I can imagine that being pretty ugly.
Did you imagine how fast you have to spin just a CD-ROM in order to get it to explode? But there's an RPM that a CD-ROM will explode at. Okay. Now, if you needed your CD-ROM to flow more and spin faster, then you would have to redesign this cross-sectional aspect of the CD-ROM so that it was stronger and could go faster. And we have to do that with turbochargers. So we have to make them, if we're going to designs that work better at higher and higher tip speeds, and we also have a responsibility to stress analyze those designs so that they're stable at those RPMs and do not deform or break.
Is this where with older design turbos, this wasn't really a thing, but also the number of people measuring turbo speed probably wasn't there either. These days it's become infinitely easier to measure turbo speed. Most of the performance turbos just have a facility already to essentially bolt a turbo speed sensor straight into. So is this where that limitation on, most will recommend the maximum speed that the turbocharger should be operated at? Is that for that purpose, or is there more to it?
It's for safety. Yeah, it's generally for safety. In a lot of cases, you're going to reach the safety limit before you can reach the flow limit. And if you're making class competitive turbos, like you're trying to make a turbo that is an inducer limited turbocharger, then it's going to just keep working better and better the closer you get to the failure point of the wheel. And the only reason that you're going to not fail the wheel is because you're monitoring how fast you're spinning it and you're staying inside its envelope that it can operate at. It's the same thing if like somebody gave you some camshafts and they just keep pulling all the way to 8,700 and they go, man, whatever you do, don't go past 87, bro. And then you go, man, it pulls all the way to 92, right? And they're like, I said, don't go past 87. You're really lucky that you don't have a problem. I don't know what you're talking about, man. It works great. It works better at 9,200 RPM. It does at 8,700 RPM. Well, the next phone call from that guy 2 days later is, you're not going to believe this, but it broke. I'm like, no, I totally believe that it broke. I totally believe that it broke.
We told you it was going to break.
Yeah.
Yeah, but I mean, I think the whole car industry is full of that kind of, if it's making great power here, well, a little bit more, it's probably going to make even more power. And even if you're beyond that limit, if it's making great power, that there's a bit of an incentive to just keep pushing until it doesn't make any power at all.
We're all guilty of that.
Yeah.
We're all guilty of that.
All right, we've focused on the bearing cartridge, ball bearings, and we've talked about the compressor wheel. I think the other side of the turbocharger, which is often overlooked though, is the turbine wheel. And I think this is another area where Xona Rotor are really doing something almost semi-magical. I think you've got your UHF ultra high flow turbine wheel. There's a bunch that goes into this though, because that turbine wheel lives in an incredibly hostile environment. So it's not just the aerodynamics of that turbine wheel that are important, it's also the material that you choose to make the turbine wheel out of. So talk to us about the evolution of turbine wheels.
So generally speaking, turbine wheels, if you go back to the beginning of air research in California years and years ago, they didn't have quite the same materials we have today, for sure. Ultimately, people started making turbine wheels in GMR and 718 for cooler diesel applications and 713C for gasoline applications. By the time you get into the mid 80s and 90s, all the turbine wheels are pretty much 713C. And then by the time you get into the late 90s and the early 2000s, you start to see manufacturers in some applications where they're very small turbochargers that are worked very hard, like you get the 1.8T Volkswagen with the little KO3 and KO4 turbochargers. That's when you started to see the implementation of MAR M247 and other MAR M style alloys, which just give you a couple hundred more, a few hundred more degrees Fahrenheit of operating temperature before the strength just noses over. So really what you have, the problem you have on a turbine wheel is that you have a lot of centrifugal force. Okay, it's the same problem you have on the compressor side. Okay, but it's less of an issue because you're using a way stronger material. You're using a super alloy like Inconel. So it's way less of a problem. But what are we doing at the same time? We're also heating it. So heat changes the strength of materials. They're related, directly related. So when we heat the turbine wheel to 1800 degree Fahrenheit and it's a 713 Inconel material, we really compromise the strength of that blade. Okay. So I'm just going to use some real round numbers here. Okay. And this is not for the geek engineer guys out there. They're going to go look up a chart and tell me what the number is. But if we're operating 200 degrees over, like say you say 713 is good for 1700 degrees Fahrenheit, we're operating at 1900 degrees and it's steady state soaks at 1900 degrees. And then you try to run it at its max speed rating, you run a strong chance of spitting the tips off, just the little tips of the turbine wheel where the gas first comes in. This is going to be the hottest part of the turbine wheel. Where the first gas first comes into the turbine wheel, you just are going to start to melt those little tips off of the end of the turbine wheel. And you'll see people put pictures on the internet like, what happened to my turbo? I didn't lose a valve. All the tops of all my pistons are there. I didn't break a ring. I didn't lose a valve guide. I didn't do anything. But what the hell went through my turbo? Nothing, man. You ran it really hot and you spun it really hard, and your turbine wheel tips just spit off like a loogie off the tip of that turbine head. They just melted and just flew off.
I have seen that, and it does definitely look like something has gone through the turbocharger, though, so I can see why there's a bit of confusion.
Mm-hmm. It looks different, okay? To the trained eye, and if you look at it really closely, there's some really big differences in the appearance of it versus impact, but you're really tempted to call it a foreign object damage at first if you don't look very carefully.
Yeah, it'd be easy to confuse the two for sure. In terms of another priority with the turbine wheel material and design, there's, compared to the compressor wheel, the material obviously is much denser. Is there a drive to kind of get weight, mass out of that turbine wheel to help the turbo's response?
You do see people experiment with that. And Mitsubishi is the first company that I'm familiar with that tried to work on that a lot. And they did work on it a lot. Made a lot of turbochargers with titanium aluminide turbine heads. They used them in some Nissan applications. They used them in Lancer Evolution applications.
I actually remember there's a number of the JDM Nissan engines that had ceramic turbine wheels, which for the performance aftermarket were a terrible idea. Not very reliable if you wanted to push them harder.
Yes, because what happens there, you have an engineering group at the OEM supplier working with the car manufacturer engineering group, and the car manufacturing group is telling the turbo engineering group what their operating conditions are. And so the turbo engineers are meeting those operating conditions for the car manufacturing group. So then Robert shows up and goes, well, we're going to put way bigger injectors, a way bigger intercooler on this, and we're going to turn a boost up about 15 psi, and we're going to run 20,000 more shaft speed, and we're going to have higher EGT. And then as soon as you do that, you're not satisfying the design constraints of that part anymore, and the head just comes off. The trouble you have with the titanium aluminide is the trouble everybody has with titanium aluminide. It's an intermetallic ceramic. That's what you would call that material. So that means the structure of it is not inherently that different than a coffee mug when it comes to the brittleness, the ductility of the part and the way it fails. It fails in a digital manner. It's all there and then it's all not there. There's no intermediate period where it's stretching, yielding, bending, trying to give you a warning. There's no creaking that happens to the bridge before the bridge falls. The bridge just disintegrates right underneath your feet. So that's the kind of failure you have with the titanium aluminide turbine heads. Either the head just disconnects from the shaft. That's one problem, because how do you weld a coffee cup to a piece of steel? Okay, you can't. Okay, so there's a series of wedge mate press brazing processes that are used to hold that coffee cup onto the end of the piece of metal rod. But ultimately, none of them are super tough when it comes to abuse. If you're in your little operating window that it was designed for, cool. But as soon as you go and flash that car and add duty cycle, that boost controller, now you're outside that window and the turbine head just comes right off.
Yeah, makes sense.
That happened a lot on Mitsubishis. Like that happened. Oh my God, Panamera. You remember the Panameras?
Yes.
The four-door Porsche. They had a version of that was offered with a titanium aluminide turbine wheel. It was their, I don't know, GT Element Q version of that car. And they ended up doing a recall on all the turbos. Man, if you had a Panamera, you got to bring that sucker in. They put brand new turbochargers on it. They took the titanium aluminide turbos off of all those cars for free.
That's got to be an expensive recall exercise for a manufacturer.
Yeah. Now today you got Borg Warner trying to do what Mitsubishi, died doing. So, like America watched Russia just fail in Afghanistan for decades. And then we thought we would do it right. Okay, so we'll go do it. Okay, Borg Warner did the same thing with Mitsubishi and titanium aluminide turbine wheels. Borg Warner saw Mitsubishi fail over and over and over again on Mitsubishi titanium aluminide turbine wheels, do recalls, replace hundreds of thousands of turbochargers or dollars worth of turbochargers, whatever the expense was, it wasn't slight. But of course, what does Borg Warner think? Well, you did it wrong. We're going to do it correct. It's going to be awesome. Okay, but I don't know if it worked out that great for them. They have a hard time filling orders. They can't quite hit the production numbers that they want to. I know, people tell me all the time I need a turbo because I can't wait for my EFR anymore. I've had it on order forever and I don't. Or I broke my second titanium aluminide turbine wheel in this Borg Warner turbocharger and I can't do it anymore. So I need to change. So I'm not a big believer in trying to find a magic bullet when it comes to turbine material. MARM alloy works really good for turbines if you want a higher temperature option, and most modern turbines are either 713 or some MARM variant.
Okay. Again, coming back to that triangle of sort of boost response, airflow, etc. Again, we've talked about the compressor side of that equation, but the turbine side, again, the power numbers that I see people achieving with a turbine wheel that's relatively speaking so small compared to what I would have thought 10 or 15 years ago we needed to get those numbers. It's just kind of, it seems almost like an impossibility. Is this just, again, development of the aerodynamics of that turbine wheel that's allowed you to get more flow out of a smaller wheel?
Not only did it just do that at face value, but it allowed us to go back into compressor wheel development and redevelop compressor wheels that took full advantage of that. Okay, so it actually led us back around to improving speed matching on the standard offering of rotor groups that we make. So when we did UHF, I'll have to tell you, man, it surprised the hell out of us too. Okay, we knew it was going to be a great idea. We knew it was going to be hot. We knew it was radically different, and we were not wrong at all. Okay, we were not wrong at all. Now you can do it wrong. Okay, so it's not just like, oh, half the blades need to look like this. There's a little more to it than that. Okay, but the concept, as basic as it is in conceptually, the result of it was just amazing for us, and it led us to have to go back and target new arrows specifically for the UHF, and it led to the current 3 new arrows that we're using: HTC Plus, HTE, and LTA.
Okay, so I mean, it probably goes without saying, but essentially we can't consider the compressor and turbine wheels in isolation. Obviously, it's a complete package, and they need to be considered together.
Yeah, a lot of people get hung up on, well, I saw the compressor map, so I know what it's going to do. Okay, I saw a pickup truck and it was black. So you're not wrong. You saw what you saw, and that's what it looked like at first glance. But how deep do you want to go into it? When you're considering your options, if you want to optimize down to the last couple of percent, you need to look deeper than that, and you need to look at matching both sides to each other. Okay, if we're trying to put 5 pounds of boost on air-cooled Volkswagen, it almost doesn't matter what we use. But if we're trying to make another 125 horsepower in the 68 millimeter turbo class for World Cup finals, that's a different story. Now we're trying to do something really specific, and the edge of having it work is like a knife's edge. Okay, it's that narrow of a window of where it's going to work good. Okay, because you're trying to create the turbocharger to do one damn thing. Okay, choke flow better than another turbo choke flows. And here's where I talk about explosion and containment. And I'm not a big proponent of turbo class racing because I don't think it's safe. I think there's other ways that we could make classes for racing that do not depend on turbocharger limitations, because what you have when you have a turbocharger limited class is you have the tendency to want to operate it at 9,200 RPM instead of 8,700, to go back to the analogy I was using a minute ago. You realize it works a little bit better. Not a whole lot, but a little bit better if I run it at 92.
And that's what you need when you want to beat the guy in the other lane.
Yeah, and if you're going down the back straight and it's banging against the rev limiter at 8,700 RPM and you're not getting past this guy, what do you want to do? You want to kill that damn rev limiter, okay? Blow the whole damn thing up. I don't care. The checkered flag's right there, damn it. Let me have the overtake button that takes that fucking limit off. Okay, so this is class racing with turbochargers. And what happens is, you get the tip speeds of the turbos get so freaking high that if they explode, the parts are very, very, very energetic. And we're not even trying to operate the turbochargers inside their safety window. People are just operating them however they want to. They're just, the wastegate's completely shut. And I could only get 73 pounds of boost out of it, but I put another 50 shot of nitrous on it. Now I'm getting 78 pounds. Okay, well, what's the shaft speed? Oh, bro, I don't know. I don't put a sensor on that shit.
Best not to know sometimes.
The fastest guys won't even fucking look because they don't want to know.
So essentially what you're saying is those turbo limited classes, if you want to be competitive, you're essentially forced to run the turbocharger outside of its operating.
Yeah. And these guys that'll sell them and they're like, hey, we just made 3 passes. We want $4,300 for it. You save $1,800 off retail, and I'm like, man, don't touch that,
dude. that's gonna blow up in your driveway idling.
Yeah, don't touch that one, bro.
Okay, let's move on. And probably one of the more common questions that comes up when we're talking about turbochargers, and this just creates a big old can of worms, essentially, is how do I find the right size turbocharger for my given engine and application? Can you shine some light onto that very ambiguous question, which we could probably spend 2 hours talking about on its own?
Sure. Well, I'll give you kind of like a very short step process to that. Okay. So the first thing that we want to do is we need to figure out how much air we need to satisfy this requirement, because anybody that's asking you for a turbocharger has something in mind for horsepower. Okay. So maybe it was a guy with a 5-liter V8 that used to make 300 horsepower and he wants to make 600 horsepower. Okay. In a first approximation, you're going to say that 10 pounds a minute of airflow for the turbocharger can generate 1 pound a minute of airflow for the turbocharger can generate 10 horsepower. Okay. So as a first approximation, you're just going to go with that. You don't know anything about this guy's VE of his motor or anything like that. Okay. So the first thing you're going to do is say, okay, so I know we're going to use 60 pounds a minute of air. So I'm going to probably pick a compressor that has something like 80 pounds a minute.
So you're going to give it a little bit of additional headroom.
I don't want him to operate right at choke.
Yep.
Yeah, I don't want him right at choke, because as soon as you sell the dude the 600 horsepower turbocharger, he's going to call you back and goes, bro, it only makes 600 horsepower. Like, well, you did ask me for 600 horsepower. So yeah, when I try and turn it up, it won't go, man. This turbo sucks. Yeah. So you got to give them an 800 horsepower turbo when they ask for a 600 horsepower turbo, or else they're not happy. So they ask for 600 horsepower. You give them an 80 pound a minute flow rate turbocharger. They're happy. And then after they get some new injectors and an intercore, they turn it up and make 800. So they're happy. So first of all, you decide how big of a bucket full of air do I need? So that's what I'm talking about, CFM, the flow rate, the mass flow of the compressor. So that is the x-axis on a compressor map. Okay. You look at most compressor maps today are advertised in pound per minute. So you look across the bottom and add a 0 to what that pound per minute number is, and that's how much horsepower it should make right there. Generally speaking, all things forgotten about. That just real generally speaking. Okay.
Yeah. This is just sort of a rule of thumb of sorts.
Yeah, methanol cars are different than alcohol cars, different than 91 octane cars, and road RX-7s are different than diesels, different than 5-valve Audi motors. Okay, they're all different, but generally speaking, that's where you start. So how much horsepower are we making? 600 horsepower. So we want a compressor that has an 80 on the x-axis. Step one. Okay, how much boost are we going to run? Well, I don't know. I'm asking you. You're the turbo guy. Okay. Well, I say, well, if you want to make 600 horsepower and it was 300 horsepower naturally aspirated, I think we're going to probably want to run about 15 pounds of boost to make 600 horsepower. Okay. Just basic common sense.
Double the air pressure, double the power, essentially.
Yeah. Double the airflow. Okay. So you want a compressor that now you've got something for the y-axis of the compressor map. Okay. Now you're operating at a 2-to-1 pressure ratio. what is the pressure ratio? A lot of times people go, I don't know what the pressure ratio is. What is that? What are these axes on this map is? The y-axis on the compressor map is the ratio of the absolute outlet pressure to the absolute inlet pressure. So it's a very basic calculation to make. And sometimes you can use a differential pressure sensor that'll even, or a pressure sensor that has two channels in it, and you can take this very directly from the compressor. And I've seen guys that, Motec guys love to do this. They'll make their own compressor map and they'll plot their points, and they'll have a scatter graph of a log, and they'll have a whole compressor map lined out, and if they've got RPM too, they even make a really pretty good facsimile of their compressor map, excluding the transient problems that you have.
I think just before we carry on, just on that pressure ratio point, I think it's one that's just worth just covering a little bit more detail, because people often relate pressure ratio to looking at what their inlet manifold pressure is, because of course that's what we're measuring for our ECU to do our tuning. But that, as an absolute pressure divided by our barometric absolute air pressure, is not necessarily our pressure ratio, because what we also have to take into account is if you've got any type of intake prior to the turbocharger with an air filter, maybe some piping, etc., we're probably almost certainly going to have a pressure at the intake that is somewhere below atmospheric pressure. So straight away you've made things worse. Then on the outside of the turbocharger, the outlet of the turbocharger, we're going to be flowing that through some plumbing. We're going to be almost certainly going through an intercooler, which absolutely is going to have a pressure drop. So then your outlet pressure at the turbo is going to be higher than what we're actually measuring in the inlet manifold. So what I'm getting at here is, depending how good or bad your intercooler is, how good or bad your intake system is, the pressure ratio that the turbo, as far as the turbo is concerned, which is all that matters, could be quite substantially higher than what we're actually assuming it is just based on measuring our boost pressure, correct?
You're exactly right, Andre. Exactly right. And so many people overlook that. You have people that have like 3 pie cut elbows welded onto their compressor housing outlet, okay? And then like 3 feet of 2-inch piping, and they're trying to make 1,000 horsepower. And they're like, man, I just can't get anything else out of this turbo. And I'm like, man, what's the pressure at the compressor outlet? And they'll tell you the inlet pressure at the tank, at the intercooler tank. And I'm like, no. Now, right before all that fucky shit you got on the outside of that compressor cover, what's the pressure right in there? Well, I don't know. I didn't measure that. I said, well, once you drill it and put a sensor there. Yeah, it's like, holy shit, Robert, that's like 12 pounds more than what's at the intercooler.
You got some work to do.
Yeah. You're operating at a 5.2 pressure ratio, buddy. That's your problem. Okay. You thought you were operating at a 3.5 pressure ratio, but you double that with your sucky air intake pipe, and you have an 80 kPa at the inlet instead of 110 at the inlet. And all of a sudden you're at a 5.2 pressure ratio, and you thought you were at a 3.5, and you thought you were on the compressor map, but you're off the page above the compressor map.
All right, so let's get back to your story anyway. I think that was worth diving into. So we know we need a compressor with 80 pounds per minute on the x-axis, and we know we're going to be operating somewhere around about a 2-to-1 pressure ratio.
And you want to always look at what's above that, right? So 2, and you always want to look at 3 or 3.5 also, and make sure that there's room to turn it up, okay? Because everybody that you ever sell anything to wants to turn it up a little bit at some point. Very few people ever turn it down. So you look at the product that you're about to buy, and you go, does it work well there? Okay. So say, yes, it does. It's like, wow, that's great. I'm at 60 pounds a minute, 80 pound on choke flow. I'm operating at 72% compressor efficiency. I'm at a 2.5 pressure ratio, and if I turn it up to 3-to-1, it actually gets more efficient because I'm running a little bit higher boost, and it wants to do that because of the design of the compressor. So great. I got a great turbo picked out here. And then somebody goes, well, there's 3 different turbine wheels you can pick from, and there's 2 different exhaust housings you can pick from. Oh, well, shit. Well, I don't know anything about how to do that. Okay. Well, so now it kind of comes back to like, well, what's the power band we're looking for? So now you need to talk about the engine. Does the engine need to work well from 4,500 to 8,000, or does the engine need to work well from 7,200 to 8,500? Okay. Because the turbine wheel that I'm going to pick to work all the way from 4,500 to 8,000 is different than the turbine wheel that I'm going to pick if all we're doing is operating between 7,000 and 8,000. We're going to operate between 7,000 and 8,000. I'm going to go with a bigger turbine wheel, because your converter or your belt drive or your CVT or your 2-step or whatever it is that's letting you only focus on 7,000 to 8,000 RPM is just going to let us go straight there. We don't need a tight turbine side to get shaft speed, because we'll have a lot of engine energy by the time we get to 7,000 RPM. So pick a bigger turbine wheel and a bigger AR to go with that. Now you need to start talking to the guy about what size converters in the car, what the gearing is, how heavy the car is, what the power band needs to be for the car. And if the car is heavy, the power band needs to be wide, and the gearing is tall, not low gearing, then you need smaller turbines so that they spool up faster and give you a wider power band. If the RPM is like strictly limited to really high RPM, then you get to pick larger turbine wheels out of the catalog that match your compressor, and bigger ARs to go along with it. Small AR, area over radius, that's the ratio of the area of the nozzle to the location of the centroid of that area away from the axis of the shaft of the turbocharger. But that A over R ratio determines the angle that the gas hits the turbine blade with. So when you have very small ARs, the gas hits the turbine blade at like a 90-degree angle. Okay. When you have a really big AR, like a 120, the gas is almost directed straight at the axis of the shaft, and it doesn't really result in much shaft acceleration. It just helps with having lots of mass flow. So if you don't need boost until you get to high RPM, then you can go with bigger ARs because you don't need to accelerate the shaft. You can't get away from accelerating the shaft because you are at such a high RPM by the time you're needing it to be in power. So you get to pick bigger turbine housing ARs and bigger turbine wheels if you need narrower power bands, and higher RPM power is where you want to focus the 600 to 800 horsepower. So you pick the mass flow, you make sure the pressure ratio is okay, then you look at the application and you decide how much turbine you want to put on that turbocharger based on how big the engine is and what the power band needs to be. And then after you pick the turbine wheel, you pick what size turbine AR you're going to use to go with it to also complement the rotor group that you just picked out. That's how you do it every time.
In terms of those two, I guess, levers that we have to pull on the turbine side, we've got the turbine wheel diameter, and then for each of those diameters, we're potentially going to have multiple housing ARs, which you've just talked about. A good way of describing that, I've kind of always thought of it as the turbine is your course adjustment on flow, and hence essentially response to the turbocharger. And then you've got the AR is kind of your lever to pull for fine-tuning your boost response in the RPM range. Is that sort of a reasonable way of describing it?
It's a great way to put it. Actually, that's a great way to put it. Yeah, you nailed it dead right on. I would totally characterize it that way. Yes.
Okay. So I guess the point there is to buck kind of some misinformation out there is there's a limit to what you can expect to achieve just by changing the AR of your turbine housing. You know, you're still going to primarily be driven by what that turbine wheel is going to give us in terms of results.
Yes, that's correct. You almost never choke in the turbine housing. You almost always choke in the turbine wheel, unless you run UHF. Then you almost never choke in the turbine wheel. The only way you're going to choke it is with the AR. So on UHF, if you thought you were going to run 100 AR, you probably ought to run at 80.
Okay. So it just steps down that much to get the same results. Wow.
Yeah, exactly. Yeah.
All right. So this all sort of leads us to a conversation around exhaust back pressure, or drive pressure as it's often called with turbocharging as well, which is one of the metrics I quite like to look at. I kind of got into this when I was drag racing, because drag racing is such a unique form of motorsport where we don't really give a shit about boost response, boost threshold. It's all about leaving the line with boost and then running the engine across a narrow RPM where we're always got the turbocharger spooled up and operating. So that allows us sort of this flexibility of running with a low drive pressure or low exhaust manifold back pressure, where I always sort of found the magic spot was where our exhaust back pressure was below inlet manifold pressure. And I don't know, I've always sort of explained this as then the engine starts almost operating like a naturally aspirated engine. It gives us the benefit of being able to use larger cams with more lift and, more importantly, more overlap.
Yeah, we call that the free ride. You call it the free ride. When there's more intake port pressure than there is exhaust port pressure, it's definitely in the sweet spot. It's definitely on pipe, so to speak, to use some two-stroke lingo. You definitely get some dynamic things happening there when you can put all the power that's necessary to drive the compressor on the shaft and have that drive pressure be below the boost pressure. You have done a really nice job with the turbocharger. Now, do you always want that? You don't always want that. Okay, you don't always need the exhaust back pressure to be lower than the boost pressure. And definitely if it's what I call an ice cream and burnout kind of car. If it's a car that you just want to have fun with and that you want to spool around town and you like some part throttle boost, you like good connection between the gas pedal and the boost gauge, then you're not going to set it up where you do free ride. You're not going to set it up where you have less exhaust back pressure than boost pressure. Like on my own 6.2 liter turbo SUV, my Chevy truck, I have a 2-to-1 back pressure. Okay. But I love it. It's great. It's responsive. The car runs 6-second, 1/8 mile. It runs, it'll run 11 O's easy at the drag strip. which is, it doesn't have a cage or a harness, so I can't go any faster than that anyway. So in a lot of applications, you end up wanting the power band more than you want peak performance at redline. So yeah, drag cars, like you say, you're going to start on the two-step, or you're going to have a really loose converter and a power glide, or you're just going to go down the track at 7,500 the whole way down. That's way different than a street car where, when you shift from, if you short shifted at 6,000 and it drops it to 3,500, I want some response at 3,500. Well, when you build a car like that, you're going to end up with 1.5 or 2 times the back pressure at redline that you had, that you didn't have to have on a drag race car. And that's good. It's not bad. It's not like the end of the world. Like, oh my God, it totally sucks and my car sucks. And but a lot of people overreact to that. Like, what, I have, but my back pressure is higher. And I'm like, but you have a street car, dude. It's a road course car. You need to come out of a corner at 4,500 sometimes, don't you? It's important for there to be something at 4,500.
And I think the internet's responsible for a lot of misconception here as well, because everyone reads stories or articles about an Evo that's got 900 horsepower and they've got a turbocharger that's sized accordingly, and it's a drag car. So they think they want that for the street. And I mean, that would be an absolute dog on the street. You'd be way faster and have a hell of a lot more fun with 500 horsepower and a power band that actually starts at sort of 4,000 RPM than 7,500. So yeah, I think that, and it's kind of that trade-off with that exhaust back pressure ratio. The higher that is, the better your boost response is going to be, and probably is going to fall over a little bit in the top end.
As a rule of thumb, that is 100% correct. UHF kind of helps with that a little bit, but that's a new development. That's a new thing. The Xona Rotor turbine wheels are kind of a new thing. So that's a little bit of an equalizer on this. It kind of lets you have both sides of it, because normally you would have to run that size turbine wheel and you'd have to run a 100 AR. But now I can run that size turbine wheel and I can run an 82 AR. So now it spools up a lot better and it has a lot better mid-range. But since it has the UHF turbine wheel in it, I'm not choking in the turbine exit. I'm trying to choke it in the housing. And I can change the housing. I can't change the turbine outlet, like you were talking about coarse versus fine adjustment on drive pressure.
Okay. All right, Robert, it's been amazing, but I am conscious of the time here, so I think we'll move towards wrapping this conversation up. And of course, we finish up with the same 3 questions we ask all of our guests. The first of those is, what's next in the future for you, for Force Performance, Xona Rotor? Maybe if you could even just look into your crystal ball and tell us where we're going to see turbo technology and what it's going to give us in another 5 or even 10 years' time.
5 or 10 years, hard to say. I know over the next couple of seasons, we're going to continue to release new arrows and continue to push this art forward with all the ability that we have. We're not slacking off any on developing new parts. A lot of new parts in development right now, and you're going to see those coming to market over the next year, 2 years, as we move out of our opening position in small frame turbochargers, and we start releasing more mid and large frame turbochargers. So you're going to see us move from just being strictly small frame stuff for smaller engines or medium power applications on twins. Like currently, our small frame turbocharger will get you to 2,000 horsepower in twins, though. So where we're going is more medium and large frame stuff. So you can see the power numbers just continue to go up from us over the next couple of years.
And that, I guess, has been something that's been missing from the Xona Rotor range, is the turbos that would be fitted to a 5-second 2JZ drag car. You don't currently have a single turbo that's going to cover that 3,000 horsepower sort of target.
No, we don't. We don't have GT55 size stuff or S500 size stuff, but that's coming.
Okay, great. Next question, is there any advice you give to a younger version of yourself to help reach where you are today in your career faster?
Don't rent the space for your business. Buy the space for your business. Okay. Because if you're not independently wealthy, most of us are not, then you need to have some diversity in what you're doing, because people want race car turbos and then they don't. Okay. So if you own property and you diversify a little bit in what you're doing, you're far better off, I think. So if I had something I could go back and tell myself when I was 30, being 55 now, I would say stop renting those buildings and find a way to buy your buildings. And that's got nothing to do with, that's probably not the answer you're expecting.
I definitely wasn't expecting that, but I mean, I'll take it.
Okay. But if you go ask your dad, what should you do today? He'd probably say something like, you need to buy some property.
I just actually liken that to our own situation here in Queenstown. We moved down here 9 years ago. The business was fledgling. We weren't making a lot of money. we had the option of 2 buildings at the time. So really there was not a lot of option. The one that we currently are still in 9 years later was available for sale at the time, and the landlord had had it on the market. Queenstown, I don't know, must have been going through a bit of a tough time at that point. It had been available for rent for about 6 or 9 months and no one was taking it. So we actually managed to negotiate a pretty good rate. And at the time, as I say, the landlord said, oh, well, you can buy it if you want. Well, we had no money. That just wasn't an option. 7 years later, and we sort of went through a bit of a market reappraisal of our rent, which at this point had over doubled from what we started with. And again, the landlord said, oh, you can buy it if you want. And at this point, we did have a little bit more money, but of course, unfortunately, the building had over doubled in value. We're like, yeah, okay, we'll just keep making courses. Don't worry about us.
Yeah. See, well, 10 years ago, you were wrong about not having the money to buy it. Okay. That's what that shows you.
I think it's a mindset as well.
Yeah, it is. It is. You think you can't buy the property, but you can.
I think there's a book that I read, and the mentality is wealthy people don't say, I can't afford it. They say, how can I afford it? And I think flipping that switch, flipping that mindset is so important, because when you say how, you start looking at, like, it opens your mind to options. Where you say, I can't, your mind's closed. There are no options. And that goes with everything, actually, I think.
Well, I mean, if you're used to making horsepower on cars, you just sit there thinking about how am I going to get it to make more horsepower anyway. And but everybody's going to tell you it can't. But your job as an engineer that builds horsepower into things is to find a way to show them that they're wrong and come up with your UHF or come up with whatever it is that you can come up with to show people, no, look, we can push it a little bit further.
Absolutely. All right, Robert, last question for today. If people want to follow you and see what you're up to, see your products, where are they best to do so?
We make content for our Force Performance Instagram account and Facebook pages all the time, and you can always see our full product listings at forceperformance.net on the internet. That's where you'll see all of our cool new products.
And Xona Rotor?
Xona Rotor, same thing. We active on Xona Rotor Instagram and Facebook, and XonaRotor.com website. Always updated with the latest products. Also on the Xona Rotor website, you'll see the compressor maps. You'll see dimensional drawings for the parts, so you can see if they'll fit in place of your other stuff, so on and so forth. So the websites and the social medias are great places to keep up with what we're doing.
Amazing. And as always, people listening will find links to all of those accounts in the show notes, just so you can't miss it. Look, Robert, it's been amazing to get some insight into your background, the product range, the technology particularly that you've got going on with these Xona Rotor turbos. And it's definitely making me second guess my current turbocharger on our Toyota 86 endurance car. So maybe an upgrade might be in the pipeline.
All right, we'll slide into my DMs, brother.
Thanks a lot for your time, Robert. We really appreciate it.
All right, boost on, Andre. Thank you, brother.
If you enjoyed this episode of Tune In with Robert Young, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Aussie Beach listener coming from, you guessed it, Australia, who's made a comment on a very specific episode, which was our Project Binky episode. He said this long-form interview was full of interesting stories and motor race information. Well done. Well, great to hear that you enjoyed it. And if you get in touch with your t-shirt size and your shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.